Okay, cool. All right. Well, welcome those of you who are here already, and welcome those of you who are going to be filtering in as things go on. This is the second in a series of COFFIES community workshops. Second out of three, and three because we have three major themes in the COFFIES thrust. The second of which, or I don't know which order they come in. There was a community workshop last week on the near surface shear layer. This week we're doing the Tachocline. So this is the October community workshop on the Tachocline. And Gustavo and myself are your theme leaders, not to be confused with team leaders, but yeah, we're the ones sort of running this workshop at least. I'm sort of trying to get everyone together. So, oops. The Tachocline, I'm not going to say anything scientific. Everyone here probably has some idea of what the Tachocline is, and we're going to have talks later on which talk exactly much more about observations and theories of the Tachocline, but we're here to talk about the Tachocline, that mysterious thin layer that sits between the convection zone and the radiative interior. That's why we're all here. In the proposal we had for the Tachocline theme, there was sort of three major goals elucidated there, and here they are. Number one, to distill the question of the dynamical origin of the Tachocline to a likely prevailing theory from amongst the many theories that exist already. Number two, to incorporate these ideas, then more representative Tachocline dynamics into dynamo models. And number three, to connect large-scale dynamo fields to the much smaller scale magnetic structures that emerge as active regions in the end. Now, these are three extremely challenging goals. So we can't do all of these today. So my idea our idea for today is to definitely ignore the third one. The third one is something which connects this theme with next week's workshop theme, which is about flux transport and flux emergence. So we're not really going to talk too much about that today. We're going to keep, how you connect or how you would implement all this into dynamo models in the back of our minds all the time, because that's our ultimate goal. But really today's primary focus is this first one, to distill the question of the dynamical origin of the Tachocline. That's what we're trying to do. So this is the primary goal for today. And really this workshop is all about how do we take the next steps from where we are now? How do we move forward from this point in time? So as we go through this workshop, we'd like everybody in the audience to have these overarching questions in your mind, which are, how do we take the next steps with respect to observations, and how do we take the next steps with respect to theory and simulations? Because it's a marriage of these two things which is going to enable us to make progress. So we'd like everyone to have these major questions, which is just the question of what are the next steps in mind as we go through all the talks today. And these next steps are what we're ultimately hoping to get out of things today. Now, many of you have seen me give lots of talks about this before. There's tons of things to do with observations. There's tons of things to do with models. I'm not going to say anything about this right now. This is a little schematic that I come up with. It sort of shows you some of the connections between some of the models that I know about, at least. But the talks today have been specifically chosen to come from a wide range of areas in this sort of diagram of all these things that are available. So Ansgar Reiners is going to start us off. COFFIES is not only supposed to be about the sun, it's supposed to be motivated by other stars to inform our information about other stars and to learn from other stars. And Ansgar Reiners is going to give us a broader picture of that with stellar magnetism in a broader sense. Charles is going to talk a little bit more about what we've known more specifically about the Tachocline from helioseismology. And then up here in the model, so that's a couple of observational talks, the talks which are mainly based about what we see and understand from observations and helioseismology. Peter is going to start off on the model sort of side by telling us about can the Tachocline be turbulent, either by hydrodynamic instabilities or magnetic instabilities, and then this is not actually the order of the talks. Lauren is actually the last talk, but he's going to talk about this idea of confinement of the Tachocline, making a Tachocline thin by dynamo stresses. And then, whoops, Lauren moved around there. Yeah, he's more appropriate down there. But actually, Valentin is the talk before Lawrence. Lawrence is the last one. But Valentin is going to tell us about actual possibilities of dynamos in a Tachocline. So that's connecting to sort of step number 2 that I was talking about there. which is essentially this idea of, you know, how does this all connect to dynamo theory? So we have a broad range of talks. The idea was to bring in some new perspectives, some different perspectives, some slightly wider perspectives, and just to try and get everyone's brains moving and stimulated and thinking about what these possible next steps to do with the Tachocline could be. Now, to collect everybody's thoughts, we're going to do this thing called Jamboards. Okay, so I'm going to just give you a quick demonstration of Jamboards, hopefully. So I'm going to get out of here. I'm going to stop sharing this one, and I'm going to start sharing something else if I can remember what I'm going to share. Let me just find it. Here it is. Share screen again, and now it's this one. Yeah, here we go. So here's a Jamboard, and all it is it's in a web browser. It's a URL. I'll give you the URL, or I emailed it to you before, but I'll put it in the chat in a second. It's just a whiteboard space where anybody, it's essentially a Google document that anyone can write to, but it just has these cute things for writing to. So for example, if you can see my cursor over here, this thing is a sticky note. So if I click on this, it brings up a sticky note, and I can write here, my question is blah, 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 whatever, save it. And it becomes a sticky note, which I can stick over here. So you can make them bigger, you can rotate them, you can do all the usual things. Up here, click them, you can delete them. So you can write on this Jamboard in this way. You can add pictures, you can add all kinds of stuff, but you can also add text box. So here I can just write some text as well if I want to this way. So this is how you use, and you know, these are all clickable objects as usual in the usual sort of way, right? I can move it around, etc. I can do whatever I want to. I think I can make it bigger. Yeah, I can make it bigger. So this is just a way of writing stuff to a whiteboard. So anybody can write to this whiteboard. Anyone who has the link to this thing can write on it. So this is how we're going to collect everybody's thoughts. So as you go through, as you're thinking of questions and stuff, write them here. So now there's actually a Jamboard for each of the talks here. So as I click, so I don't know if you can see me, I'm clicking to the right here. Oh, these damn spam callers are calling me again. There's one for each talk. So conceivably, it would be nice perhaps if you wrote questions specific to a talk in the Jamboard for the talk. But you don't have to do that. I mean, there is a general one at the beginning. You can always just write it here if you want to. It doesn't matter. I'm not going to fine anybody for writing things in the wrong place. But yeah, if you have a specific one for a talk, if you can find that Jamboard and write away on that talk, that would be great. And that's about it. It's just a way of writing things down. It's just a little bit of a better and more permanent way of keeping things than having them in the chat, because the chat tends to go by and then you can't scroll back through the chat very easily and you can't see it. So this is just a way of keeping things more collected. And I'm happy to help anybody with that if you have questions on that at any time. Just back to here. So that was Jamboards. Like I said, keep these overarching questions in your mind when you're writing on the Jamboards. The talks themselves are going to be 45 or 30 minutes. And they're always going to have 10 minutes for discussion afterwards. And then I'm always going to try and give people a 5-minute break before the next talk, so you can have a little bit of a moment of downtime. So the 10 minutes after talk, I mean, yeah, use for specific talk questions. You don't have to write your question on the Jamboard. You can stop and ask your question. I mean, we encourage you to orally ask your question after the talk as well. One of the good things about the Jamboards is it lets everybody have a voice, and you know, people can essentially talk in parallel, right? You can ask questions in parallel by writing them on the Jamboard. So you can get more questions out there, even if we don't have time to answer them immediately. And it also allows, you know, so it makes sure that there isn't just a few dominant voices in the conversation. It allows everyone to converse. So we encourage, you know, junior people, students, postdocs, everybody to sort of get their questions out there. And this is a nice way of doing it anonymously. If you're not comfortable asking a question orally, then this is a nice way of being able to get your voice out there as well. So please do that. But if you are comfortable asking questions, you know, orally, then please do at the end of the talk, and we'll use the 10 minutes at the end of the talk for, you know, vocal discussion there. And if nobody's asking a question, we can look on the Jamboards and see what questions or thoughts are up there and discuss those too. Keep these overarching questions in mind. Feel free to write on the general board or on the specific talk board. At the end of the day, we're going to have a more general discussion. We're going to break into multiple groups and generally look over the Jamboards and sort of talk about what's been in our heads for the day. And there's going to be, it's not very long. It's only like 20, maximum 30 minutes, just for people to get together and chat about what they think are the overriding principles that have come out of the day. Maybe we would try and cluster things, cluster ideas, and try and sort of pick out what are the main things that come out of that. And then we'll regroup as one big group to sort of, once again, go over those ideas and try and pick out the main things of the day. So that's pretty much how it's going to work.
Nick?
Yes, I hear a question. Peter.
Yeah. Now, when we're underway, how do I access the Jamboard? What will I see that I can click on to use it?
I'm about to give you a URL, and all you have to do is click on that URL so that you can go to in a web browser, you're in a Jamboard. So it's not part of Zoom, it's a separate thing which will come up in a web browser.
Oh.
Okay?
Okay, so I'll need a separate screen for that.
It'll be on a different window than your Zoom window, yes.
Yeah.
And don't worry if you don't want to use it, Peter. Write in the chat on Zoom or whatever, or ask questions like you normally do. It's okay. There's no penalty for not using the Jamboards. It's just an easy way for people if they want to.
No, sure. I got distracted.
Yuri, hi Linda, nice to hear you, Linda. I recognize that voice. Okay, I'm going to stop sharing. I'm done. If anyone has a very quick question, I can answer it. I see we're up to 34 people. That's better. Okay, I don't see any questions. So I think it's time to go, and it is time. Okay, our first speaker, like I mentioned a little bit earlier, is Ansgar Reiners. Ansgar is from Göttingen. So we're putting Ansgar first because he's very important and we're very happy to have him here, but also because it's late for him. So we don't want to keep him away from other things on a Friday night more than we have to. And like I said, Ansgar is going to give us the first talk, which is a more general stellar magnetism talk. So the relevance, we're trying to broaden our views of tachoclines and stellar magnetism. So this is awesome. So Ansgar, you want to share your screen and off you go?
Yeah, thanks.
Awesome, thank you. You have
I'll do
40
this.
minutes plus 10 minutes for discussion.
Okay, thank you. I suppose you can all hear and see. Yeah, thanks for having me. And I will give you a little broader overview about stellar magnetism as was discussed. And I also thought, well, I asked myself, how can I inform this crowd? So you certainly know a lot about this. I'll give you my perspective on magnetic field observations, and I'll throw in a few more words on my thoughts from the observational point of view on cycles. And well, I asked myself, what kind of observational evidence do we have for a tachocline anywhere, or for the non-being of a tachocline, particularly in supposedly fully convective stars? So I'll throw in a few slides at the end for this. Also, I would like to encourage you to just ask questions during the talk. So if anything is super important for you, or you think you don't understand what I'm talking about, please let me know. Perhaps Nick, you can observe the chat or the Jamboard if there's any immediate questions and people don't want to write, people don't want to check. I'll probably not see this as I go along. So I don't need to introduce the importance of magnetic field observations for the question of a tachocline. So I'll just go forward and talk to you or tell you one of the observational sort of crutches that we usually use to inform us about magnetic fields. So of course, we all believe that magnetic fields are sort of the underlying reason for everything we know about stellar activity. And this is something that I just skip because I suppose that you all know all about this. Nevertheless, what we've done mostly, or what is observationally a lot easier to access, is chromospheric and coronal activity. So calcium-2, for example, H-alpha, helium, or X-rays are indicators of stellar activity of magnetic fields that may or may not be produced in the tachocline. That we can observe in other stars, and that have been observed for a long time, and we have observed periodicities of those cycles, and these cycles, of course, they may or may not be connected from a tachocline. I think the general the general picture, the broad picture is sort of that if you have a cycle, well, you probably believe it's coming from a tachocline or not. Some people may or may not, but this is certainly some ingredient of observational information. And then also how are fields ordered, how are fields emerging on the surface, what kind of field strengths do we have, what kind of distributions. And on the lower right, you see the magnetogram. So for the sun, we know this, and we know that where we have magnetic fields, positive and negative polarity here in bright and dark, we have also chromospheric activity. And there's a lot of information about activity, as I said a few times now, but there's not that much about magnetic fields. And I will not go too deep into the question how we do measure magnetic fields. This is something, I do have slides about this, so we can go into this a little deeper later if you want me to, but I'll skip a large part of that. So I will mostly concentrate on the results of a paper that we recently put out. And I think that is sort of makes a new step in this observational picture. So we were actually able to measure magnetic fields in many stars, lots of stars, main sequence stars, very similar to the sun and different than the sun. And I'm going to summarize these results. And if you have particular questions about the methods or something, just let me know. So I'll start right away with the most with the picture that we have in this plot that I think is essentially showing our observational picture of stellar activity right now that sort of combines most of the information. This has more than 300 stars measured magnetic fields in them. On the y-axis, you see the average surface magnetic fields that we measured on those stars. And not only we, a few other people also, of course, contributed to this, but most of the results actually come from a survey that we carried out. And I'll show you a few more details about what we did here in a second. But I want to focus first on this plot, since this is the most important plot of the talk, I think. So y-axis is average field strength. This is the average over the surface. So the sun lives somewhere down here. The sun is, I think it's probably this symbol here, one of those. So we put something like 120 or so Gauss. You can argue whether this is larger or lower, depending on what kind of measurement you believe. And then Rossby number, or maybe it's actually one of the other signals. I don't quite exactly know, but it's one of these things here. So the sun has an average field of, say, 100 Gauss or so. And then you immediately recognize what you probably know, that there are lots of stars that actually have average fields that are as strong as the sunspot center fields are, several kilogauss. That is not new, that has been known before. And but now all these measurements that we put in this plot here show us that we have two groups again. So this kind of diagram is something that you know from the well-known stellar activity rotation relation, and I'll show you that plot a few times later. So where we compared chromospheric or coronal emission to the same entity down here, which is the Rossby number. So this is the observational Rossby number. Theorists, of course, have a precise definition of what a Rossby number is. And here, this is just some kind of observational analogy. So it's also comparing rotation timescales to convection timescales. It is simply the ratio between the rotation period of the star and the convective turnover time of the convection zone, whatever that means. And by whatever that means, I really mean whatever that means, because we have essentially no idea what the convective turnover time in the star is. There are many questions you can ask about the definition of this thing, and it came up sort of course, from a more or less well-motivated theory about what all the stars should do, namely that they should sort of organize whatever field they grow with according to this ratio here. And you can argue that this may not be true for most of the stars, or it may, and this is not what I really care about here from an observational side. The main motivation to use this number is a rather empirical one, and that is it works, right? So people have spent a long time on sort of sorting out trends and dependencies between chromospheric coronal emission and stellar parameters. And it turned out that you can find a value, tau, convective turnover time, you can fit this number to sort of make this relation here appear as sort of a relation, right? So that stars actually group similar to this here in other plots. I'll show you another plot where this becomes more clear. What I'm saying is that if you do this, if you look for a number that sort of brings you some ordering in all the mess that you can observe from stars, you find that what you need is a convective overturn time that sort of scales with 1 over square root of the bolometric luminosity. And that is something that that is close to the expectations. Expectations is a bit of a different exponent of L ball to the exponent 1 minus 1/3 or something. Minus 1/2 is what we sort of see observationally, and you can argue whether this is the right scaling or not. But this certainly is very close to what we need to make this relation come out as clear as you can see it here. It's a lot clearer in coronal emission. So what we've done here is we essentially took the same tau and we computed rho for all these stars. You can see the blue stars are all on the left-hand side of rho equals 0.13. That is fast rotation. So these have slow rotation periods. Rho is p over tau. They are fast and these are slow. So in this diagram, blue and red doesn't really make a lot of a difference or make a lot of sense because you can see it easily, but this color choice will be used later in different plots as well. We fitted 2 power laws here to these clouds of points, and of course we can argue that this may not really be what these stars do. There's a lot more scatter, of course, but yeah, measuring magnetic fields is something that comes with a lot of scatter, and who knows what other trends go on. So this is the first approximation. And then we have the size of the symbols and the brightness of the symbols that goes with stellar mass. So we have a wide variety of stellar masses here, including solar mass, 1 solar mass stars, and down to like 10% of solar mass. And we will see that distribution later. And so what I'm arguing is that we have one group here. These are the rather slow rotators where the dependence on rotation is a lot steeper. And then we have one group here, the rapid rotators, that also do show a trend. So this is statistically significant, and you can say, yeah, well, who knows about statistics and this scatter? There's a lot of scatter here, and I do agree with this. I believe we also see this trend in the chromospheric activity, coronal activity, as I will show you later. So we argue that, well, there seems to be a trend as well here in the rapid rotators, which is kind of interesting, I think. And yeah, this is really condensing most of the information. So I would like to briefly talk about what we did here, because it's quite nice. So we are using data from our Carmenes survey. Carmenes is a spectroscopic survey that looks for exoplanets around M dwarfs, actually. And we've been observing more than 300 stars for like 5 years and more. And we collected about 20,000 spectra, and about 15,000 of those we were using. So this plot that I'm showing in the background here, that really contains information from more than 15,000 individual spectra. With 2 spectrographs, actually. Carmenes is 2 spectrographs. It's a visual arm and a near-infrared arm spectrograph covering wavelength ranges from 550 nanometers up to 1.7 micron. And that is really a lot of data. And this was necessary to get all this information out, because you need very, very high spectral quality. We corrected for telluric contamination. So all the spectra that we were using were individually, of course, automatically at some point, but individually corrected for telluric contamination. And what we did is we applied a multi-component polarized radiative transfer model to fit our spectra. And how this looks, I show you here in an example. These are, this is one particular star and many different individual spectral lines that we were using to constrain the information about the magnetic field. We use the Zeeman broadening, essentially. So if the star has a magnetic field and the line is formed in the presence of a magnetic field, the lines become broader depending on the Landé factor the individual lines sort of show. And it's important that we always have at least one line in the sets that has a 0 here. These are the individual Landé factors. And these lines, the width of the lines, the dependence on the width of the lines on the magnetic field strength depends on the Landé factor. And for this line, for example, this line is not sensitive to magnetic field at all. So this is a great calibrator. This needs to fit in the first place to actually get the V Sini wrong, the rotation of the star wrong, and everything else right, that you need to make this fit. And then in all the other stars, you get information about the field itself, because you can fix the rotation and a few other parameters from this line here. And what you see here, what I want you to see is the difference between the red line and the blue dotted thing here, which is also a model. The blue dotted model is the model that we would see, or the line that we would see if the star had no magnetic field. And you can see that here they lie on top of each other. And in the other stars, in the other lines, they are very different. So here you can see the effect of the Zeeman broadening. The red line is broader than the blue dotted line. And for all the different lines here, the effect has different strength, different intensity. And this is how we determine the field strength. And it is also possible from this to determine some kind of distribution of different magnetic field components. So what we do is we actually assume that all the stars have components of different magnetic field strength. And we sort of choose the choice of field strengths that our model is able to pick from, according to a few other parameters that need to be optimized in some way. But a typical example, and looking a bit behind the curtain, is this here. So I want you first to look on the lower right-hand side. This here is the distribution of field components for this particular example. So we offered field components in steps of 2 kilogauss. So they need to be sufficiently different in order to make this work in the first place. And the model comes out with a broad distribution here. Most of the star is distributed or is covered by a field with a 2 kilogauss strength, and then 4 kilogauss is a bit less. And then you can ask the question whether this is significant or not. And there are some error bars here that you can see. There's of course some relation between the parameters, some degeneracy between the different strengths, and that is what is supposed to be contained here in the error bars. Now, I show you on the left-hand side the obligatory corner plot just to confuse you, because this essentially shows that how things work. These are all the free parameters. The free parameters we have are the different filling factors, and you don't need to see this really. What you can see here is that these are all Gaussian distributed. So I try to convince you that the field is in some sense stable. The only important thing here is this distribution that I made larger here. This is the distribution, the posterior distribution of the average field strength that comes out of the MCMC chain here. So we have a field strength of 3.3 kilogauss on this surface on this star. And okay, there's an uncertainty of a few hundred gauss, and then you need to add a few systematics probably, and that provides you with the error bar. Important information. There's a lot of degeneracy between the individual components here. Nevertheless, it turns out that the average field on the surface, the sum that we get out, is rather robust against redistributions of components between different field strengths. Okay, so this is what is shown here. So we have a number of different models here that actually count that would actually produce a good fit, but the final distribution of the average distribution on average B is rather narrow. You can see it's a plus minus 125 here in this case. So this is how we measure things. And now I want to go a bit more. Show you a bit more how this looks in the distribution of stars. So here's a period mass or mass period diagram. We have all the stars that we've measured and added with a few more results from the literature as the circles. Here are some literature results that we took from other papers, and all the circles are our measurements. So it's a function of mass and period. The sun lives here, so it's 25 days, 26 days, whatever. Rotation period, and it has the mass of one sun. Okay, so we're here, and then the lower mass stars are down here. Now, you also see a lot of gray circles. These are additional stars that are known, for which the mass and the rotation period is sort of known, but for which we don't have magnetic field measurements. And this is mainly to show you that the distribution that we provide is sort of following the distribution of all the information that is available, just to check that we are not introducing some systematic bias from our choice or from our method. So our method might not be able to, I don't know, measure fields in a certain group of stars, in particular here, and we may have a gap there, but you can also see that there's a gap here in the gray points, right? There's a few gray circles here, but there's a lot more gray points everywhere else. And so this gives us a bit of an idea of sort of how complete we are in different areas of the diagram here. Of course, I mean, we are not making any claim that we are complete in any sense, because these stars that we've been measuring, they are from an exoplanet survey, for which we also did not really imply any obvious biases. But I mean, as of course this business goes, you sort of pick the brightest and sort of you introduce a lot of biases, and this is why we check this here. So what you can see, of course, is the sort of well-known development of rotation that we know in stars. So typically stars start out as rapid rotators. So if a star gets born with a certain mass, say 0.5 or something, so solar mass is around here, then it starts when it's young at some high rotation rates, small periods, and then as it evolves, it typically does not really change that much in mass, but it sort of travels up here vertically in this diagram. And what we can see is that the magnetic field during that adventure diminishes. And this is not very new information. This was all expected and known, but we can nicely see it here. And what else you can see is that there's essentially the size of the symbols, which are showing you the strength of the field, the size of the symbols and the darkness of the color, sort of goes along diagonal stripes here, which are essentially showing the Rossby number. And that is essentially what I've shown you in the plot before, that there's this kind of relation. So this is the way you want to look at it if you are interested in the development of the field strength. And again, there's not much news here. It is essentially confirming what we've all supposed, that all the development that we see in rotation periods, in activity and chromospheric coronal emission is consistent with the picture that this is all governed by the magnetic field strength, which is proportional to the rotation of the star and then weakening over time. So this is essentially consistent, but I think this is fitting in a crucial, a very important part of the puzzle, piece of the puzzle that has been missing. So we have not been really able to see these magnetic fields before in such a large sample of stars. Now, the question, how does that go together with chromospheric and coronal emission, is very important, because there has been a lot of work on that. This is a famous plot that you probably all know that combines X-ray luminosity to magnetic flux, and it has been shown in that paper that this relation between Lx and magnetic flux is showing up across many orders of magnitude. And so X-ray luminosity and magnetic flux go together. So coronal emission scales with magnetic flux. One thing I want you to realize is that R square is actually proportional to R square, right? And there's an R square in the magnetic flux, which is 4 pi R square B. And there's an R square here as well, because Lx scales with the size of the star. So one question that interests me is how much of this relation here is actually due to both being proportional to R square. So if we want to look into this, we need to look into the values B themselves. So how much of this is really the magnetic field itself, and how much of this is, or the relation between emission and the magnetic field strength, and how much of this is sort of just a general trend over many orders of magnitudes that obviously goes with the size of the particular emitting pieces that have been shown here. Some of these are stars, entire stars, and then down here we have individually resolved regions of the solar surface. And if you look into this now in our sample, we have here the same diagram as before, but Lx over magnetic flux. and we can see that there's a nice relation. And you can see that this is true for stars of very different rotation rates. So now the colors really give you some information about how well the relation between chromospheric emission, coronal luminosity, and magnetic flux, how much that is affected by rotation. And you can see that it is not at all, right? So there's all the groups show the same clear relation. Same shows up in H alpha, very, very tight, and also in calcium. And in calcium, we did a little trick that we had to apply, and I will show this on the next slide. But essentially, we can make this all fit together. And okay, yes, we sort of see that the luminosity in whatever activity indicators goes with the total magnetic flux of the star that we observe, which is a very important addition as well, a very important check. Again, it's not new, but it is a very important check on the level of detail that we are providing here. These are the relations that you don't have to know by heart, but here I have the same diagram and I overplot our relations here. So this cloud here is this cloud here. So the plot in the upper right of the figure is now fitting in exactly here. And you can see that there's some offset to the line that we've seen before. It is not inconsistent with the other stars up here. It is showing that there's something more going on than just a straight line here. Okay, and that's what I mean by, okay, lots of this, the general trend probably can be explained by R square, but there's more to this. And we can look into, or we can now ask the question whether the specific emission, so the normalized luminosity, normalized by the radius, or even by the temperature, by the bolometric luminosity, whether that is proportional in some way to the magnetic field strength, or to the field density. And this is what we've done here. So now we are showing Lx over L ball, LH alpha over L ball, or L calcium over L ball as a function of the average surface field strength. And you can see that this works quite well. You might be able to see some trends or not. I don't know. There may be a little group here. This may be, I don't know whether these are particular stars or not. There's definitely some grouping now here of rapid rotators and non so rapid, obviously, because we've seen that in the very first plot that I showed you. There's also a fairly good relation here between H alpha and B, and calcium is a little outlier, I would think. And so this is a little more scattery, and you can make the argument that, okay, maybe we see something here, so maybe there's a trend here with a lot of scatter, but this trend definitely does not go on, otherwise you would end up here. So there may be some saturation or not, I don't know, but this turns out to be, this might be rather interesting, and our takeaway from this is that there's some saturation in the generation of calcium emission, because what we did to produce the other plot, and I will jump back in a second, we were sort of assuming that the maximum field strength so that calcium emission does not grow stronger after the field has sort of reached a value of 800 Gauss on average. So this means that we would assume that as soon as the star has a certain general level of activity, calcium is not really increasing, and that makes this plot appear here so nice between the luminosity and calcium and the magnetic flux. If we do not do this, these blue points move over to the right and they don't fit anymore. And you can say, okay, maybe they just don't fit and everything is sort of broken. Our attempt to sort of fix this was to say that there's a field limit here beyond which calcium is saturated, simply because there's no more energy that you can additionally put into the emission than you have done already at 800 Gauss, sort of. Okay, so this is, of course, very closely resembling this figure that I've shown you. This magnetic field rotation relation is very closely resembling the well-known stellar activity rotation relation. And just to make the point, because this is the Tachocline meeting, I'm repeating this plot here from Wright and Bragg 2016, where they have shown that also fully convective stars actually fit onto this line. I tend to argue sometimes that this was actually, that there are a few more fully convective stars in this plot here, and this is not really, these are not the only ones, but we don't need this to discuss this at long because it matches. Okay, so there's no difference between partially and fully convective stars in the rotation activity relation on the left hand side, and there's also not an obvious difference between partially and fully convective stars here. So the very small symbols are the fully convective stars. And there are many of them here in this cloud. And of course, you can say, oh, maybe there's something going on here, and maybe there's some trend. And yes, we can look for this, but the data quality and the amount of data points, this is not clearly coming out. Of course, this was something that we've been looking for, and we would like to have said something more about we found something, but we couldn't convince ourselves that there's anything significant going on. Okay, so I would like to briefly remind you of the rotation activity relation that we've known. I'm showing the same plot as before. Let me go back 1 second. So this plot here, Lx over L ball over rho, this is essentially what we've seen here as the rotation activity relation, and that resembles this plot on the right hand side. Now you can draw this plot on the left hand side in different colors and with different names, and you get this thing here. This is exactly the same plot as before, just from a paper that I was responsible for. And so this is the same number here on the y-axis, but here we sort of used a slightly different way of writing things. But if you identify r to the -4 with the square root of the bolometric luminosity, you find out that this is essentially the same thing. And this was something where we tried to minimize the scatter here around these gray lines. And we argue in that paper that there's also here a trend going up, which sort of is not shown here, but I would argue that this cloud here is a lot higher than that plot above the dashed line. So that there's also this rotation dependence in the rapid stars. And we asked ourselves, what could be the reason, the physical reason for what we do, what we see here? And we were sort of not really seeing any obvious way to sort of produce this thing here as a dependence on the Rossby number and a broken power law in X-ray over L ball. So what we came up with is this idea. And for this crowd of stars here, this is exactly the same as before. So we have now rotation period on the x-axis, and we have on the y-axis here Lx over L ball. If you say there's not much happening in Lx over L ball, you can plot it against anything, whether you plot it against the Rossby number or P, it doesn't change much. And that's essentially what we've done here. So these are now the stars that have a certain Rossby number below a certain limit, rho 0.13. They are just plotted here, nothing happened. And for the others, we simply chose to not plot them against rho anymore, to not plot Lx over L ball against rho anymore, but we simply decided to plot Lx over P, which is essentially the same as we did before when we asked ourselves, well, is the R square proportional to R square thing something that is also in here? Let me remind you, just to make this clean. So we had Lx over L ball over rho here, which was P over tau, which is here L ball. So there's also an L ball in here, right? So you divide both axes by L ball in some way. And we took that out by simply plotting Lx over P. And you can see that this is also producing a nice form. And this is what we sort of advertise in that paper, that we think maybe the saturation comes in as soon as these stars reach a certain maximum level of normalized emission. They just don't grow anymore, and then they are saturated. But as long as they are not saturated, they actually grow Lx as a function of P, which are two observables. So this makes the whole observational picture a lot cleaner. This doesn't rule out that the Rossby number is the underlying reason for the whole thing, but this sort of adds some opportunity to think about the theoretical background here. And from this, we can come back to our observations of magnetic fields, and we can make the same translation and ask ourselves whether we could actually also produce this plot here for the magnetic fields. And this would go like this. So for the saturated stars, the fast ones, you would still want to plot the average field, but then normalize it by the maximum amount of the field that you can get. So this is sort of the saturation level. And we chose to use average field over the maximum, what we call kinetic field limit here. And that you can see is sort of pretty much the same. So they all seem to saturate at something that we call the kinetic field limit. And for the slow rotators, they follow a relation to the rotation period of their magnetic flux in this case. Okay. Now, whether this is what is relevant for the physical explanation or the other way to show it is something, of course, that from an observational standpoint is moot to discuss. But that it may be interesting to think about theories of dynamos and this. Where do we get the kinetic field strength from? This is actually from geodynamo models. There was some work from Uli Christensen and people, and I was involved here in the comparison to stars, where you can say, okay, this is sort of what we take as convective field limit. And if you compare that to the measurements of the field and of the total magnetic energy we see in different objects, you can make the point that there's a proportionality, and this proportionality is valid for planets of the solar system, for rapidly rotating planets, and also for the saturated stars. And so this is the model that we chose for the kinetic field strength limit. And this apparently, well, according to the plot I showed you before, provides a sound picture. I'm not going so far as to say that this is how it works, but I think this is worth or could provide important or interesting information to put together a picture of dynamos. Okay, and then finally I have this plot. So from force balance, you would predict something that goes like the equation to the left. So the magnetic energy should be proportional to the kinetic energy the star has, divided by the Rossby number. And if you plot this, well, you get this kind of thing here. And you can say, yeah, there's a trend, or you can say, no, there's too much scatter. And I leave this to you to decide. There's certainly interesting trends with colors and symbol sizes that may or may not be relevant and to look for if you want to check with your favorite dynamo model. All right, this is essentially what I wanted to say about the stellar magnetic field measurements. I didn't go into polarization measurements and anything, and we can discuss that at length if you want me to. This is sort of, I think this is the most complete and consistent picture. This is a very, the comprehensive analysis of all these stars have been done in a consistent way, and I think this is a high value of the objects. Whether there's a factor of a few 10% or so in the absolute field strength, more or less, that is something that may go on, but all these plots, they do not mix together results from vastly different kinds of methods or so. So this is all very consistent and all this is everything that I've shown you. All the literature values as well are following the same methodology that we had, in particular, including lines with Landé factor G, and so we've tried to be very careful here to include only stars where we really believe that the field strength measurement tells us something about the actual field going on there. Now, I was saying that I would like to say a few more words about my observer's point sort of on stellar activity cycles, and I will do this here. So just to give you a thought on what I think about activity cycles. These are, so we've seen and we are seeing lots of papers saying that activity cycles are sort of following a scaling between rotation period and activity cycle period. And there are different branches being discussed, active branch and an inactive branch. And here's something from a paper that we wrote a couple of years ago, where we actually re-investigated the Mount Wilson sample and spent some time on trying to find all the periodicities that have been reported about cycles in that paper. And we sort of grouped this into 3 different groups, and everyone who has done this essentially did this kind of exercise. There are groups where we see absolutely clear cycles. This is something that I would definitely identify as a like it's a 10-year long or 8-year long cycle here. This I think is quite clear. And then there is something where I would say, okay, if we want to take this as a cycle, I sign, but who knows what's going on tomorrow on these stars. And then there's a group of things that is this here. So you also in the periodogram, you see some clear periodicity, and you might actually want to see this here as well. But I have a hard time making a bet on that cycle. So again, who knows what we've seen here. And if we translate this into the classical way of showing the cycle period against the rotation period, asking the question whether they have anything to do with each other, we see it like this. And overplotted are the sort of canonical active and inactive branches that have been brought forward in several papers. And so the CA things here, the really clear cycles are the red ones. The sort of medium clear ones are CB here, and they are actually connecting the points where we have 2 cycles in these, and we're connecting these 2 cycles. You can pick one of those, so you can see it here in red and blue. You can perhaps choose between the 2, and then you get this picture. And then all the ones where you would say, well, let's take some more data and wait a bit longer. They are all the black ones. So and what I take from this is, yeah, there's a group of points here. The sun is at a different part, and I don't know. I'm not really buying this active and inactive branch thing. I'm not even buying any branch thing because there's a cloud of points that I see here. I'm not saying it's wrong, but as an observer, I'm usually trained to look at sort of what the data really tell me. And at least this plot doesn't tell me that stars really do something fancy with 2 branches and that they actually know about all this. This is something that I'm not sure about. You can plot this in a different way. This has often been shown. So this ratio between cycle and rotation period as a function of Rossby number, and usually people come up with these 2 branches, and I really don't see them. So again, I'm not saying they are not there, and maybe we get more data and better data that are showing this. There are a lot of data out where we see clear periodicities, and we also see some rather clear cycles in fully convective stars. But this kind of scaling stuff, I am taking this with a lot of caution. And then a final point that I want to make, third and completely different, is something that I think is often transported, but is a misconception. And the misconception is that low mass and fully convective stars are typically very active. And this has to do with the different structure of the star. This is not what I think we see, or at least we can explain the high activity of fully convective stars in the typical activity lifetime picture. So what we know is that the lifetime of activity, the spin down timescales of the stars, grows with lower stellar mass. And yes, you may say that around here, which is where stars become fully convective, to the left-hand part here, these are the fully convective stars. You may argue and you may say that, yes, they are more active. But the reason they are more active is they are all, as a bunch, rotating more rapidly. And the reason, I believe, why they are rotating more rapidly is that they are smaller. So this is an HR diagram, and you can see here what happens to the main sequence. And the main sequence makes a turn here that you can't really see, but if you overplot beta measurements of this, you can see here where the Tachocline is actually jumping in. This is sort of where stars become fully convective and are restructuring. So the way the temperature of the star, the relation between the mass of the star, the radius of the star, and the temperature, this changes here when the stars become fully convective, and that makes this kink here. Okay, so these are fully convective here. And that means that these stars to the right-hand side of the fully convective boundary are significantly smaller than the ones on the left-hand side of the fully convective boundary. And that leads to a breaking efficiency. So that is the angular momentum loss rate that I've shown you here, and we don't need to go into this, but what you see here is essentially that there's an extremely high component of this angular momentum loss rate that scales with radius. So the larger the star, the more rapidly it loses angular momentum, the more rapidly it loses activity. And that leads to this drop here right at the fully convective boundary. And that means the stars are a lot smaller here on the left-hand side. And that means that they are a lot longer active. And without any restructuring of magnetic field generation, this could explain, or this can explain why we see that lower mass stars are more active in general. This, of course, does not exclude anything about the importance of the Tachocline, but as a general summary, so far as an observer, I fail to see the obvious evidence for the importance of a Tachocline for magnetic field strength measurements, for activity rotation timescales, breaking timescales, and even for magnetic cycles. I'm not saying it's not there. I'm just seeing we need to go on and look harder for this and find good discriminators that can actually give us an answer about this. This is, I think, essentially what I have summarized here on this slide. Thanks.
Thank you, Ansgar. That was awesome. Very stimulating. There's been a bunch of questions in the chat, and there's one hand raised from Lauren right now. So let's try and go through these in order at least. So from the chat, Peter had a question first. Peter, do you want to ask your question? I can read it if you want.
I think what I asked is whether you can say anything about longitude, latitude distribution of stellar activity.
Yeah, that's a good question. So from the measurements that I've shown you, from the Zeeman broadening measurements that we did, there's essentially no information about the spatial distribution of the fields. Of course, you can get this from Stokes measurements, from polarized measurements, for polarization measurements, and I've not touched this on this in this talk here. So yeah, this would be probably 2 other talks, and these talks I think they would not be, or at least if I would give them, they would not be about how stars and their longitude latitude distribution actually look like, but it would be about how significant are our measurements, how sensitive are we actually about measuring those. And what I'm trying to say is that without blaming anyone who's doing this, and I'm part of this, so measuring the distribution of fields on other stars, using Stokes V measurements and even Stokes Q and U, I don't think we have a clear understanding of what we're actually doing when we do this. So you can hide a lot of magnetic field on the surface of stars that you are not seeing, and of course you would be able to see. You would see the question about persistence of longitude-dependent patterns. That is something that one could potentially see if that is changing. Nevertheless, whether you actually can attribute it to really the changes in longitude or whatever effects you have is very difficult. So what I'm trying to say is that we need to be really, really careful about interpreting these geometry measurements. And I don't think I can make a very good statement about what is actually happening on stars. Sometimes we have some evidence for flip-flop effects, for sort of cycles that actually change their polarity. Everything I think so far is essentially consistent with the picture that we get from the sun. And I'm not sure if there's a lot more that we can say at this point.
If you know the rotation, something about the rotation, then you can estimate how long it takes a given feature to rotate across the disk. Is that a way to go?
Yeah, this differential rotation thing has been tried very often as well. I agree, and this is certainly a way to go. Again, there are a lot of things going on. Stars, spots come and go, and then they are differentially being sort of torn apart. And all the information about geometry, well, is one step more complicated than what I've shown you. So I've tried to sort of summarize the general picture, and I would still argue that that the patterns that we see in all the Zeeman Doppler imaging maps are difficult to interpret and as a general picture, as a general behavior at this point.
Okay, great. Paul, I think you're next.
Hi. My question was regarding the calcium K saturation, which you talked about. I was wondering, is there a connection to the field becoming faculae dominated to spot dominated? I mean, we would expect that the calcium K emission is mostly coming from structures like faculae. So if there is spot going to dominate at a certain point, then you would see a saturation. Is that expected?
I'm not sure I can follow how this would be visible in the total emission map. So what you would expect is that if you follow the rotation periods, that there's some kind of phase flip, right? That is what people have observed, or at least try to observe. How would we see this? I mean, I agree, if there's a saturation, this would be something that we could see. And one interpretation of the thing that I've shown you of the saturation could be that this is a transition from faculae to spots. But I don't think we could actually really distinguish this from a different sort of saturation. Or
all right.
Is that what you mean?
Yeah, fine. Yeah. I have a related question. So I would imagine for all the magnetic field measurements, you would be kind of weighted towards the bright structures on the star, like faculae, rather than dark structures, right? I mean, is that taken into account when you interpret field strength, which were very high at very active stars?
No, this is really a huge observational bias, and this is probably one of the most important systematic errors that we have. So if we have systematically, like we know on the sun, darker areas with strong field strengths, we would systematically miss them, which would mean that we are actually providing lower limits for the field strength. That is totally true. And I'm actually working on a different data set where we have even better data quality, and I'm trying to incorporate different sort of fields of different temperatures for the different areas. And yeah, I mean, you can easily imagine what comes out there. So the more you turn down the temperature of the high field areas, the higher the average fields get, right? So you can play around with this. And yeah, I fully agree. This is one of the major uncertainties in what we do here.
Okay, thank you.
Lauren, you're up next.
Yeah, I had a question about the Rossby number. Is that still, do we think the parameter, I mean, do we need the Rossby number or whatever this empirical parameter is to collapse the activity rotation relation? Or it seemed, I think if I understood correctly, it seemed like you could just use the rotation period to explain at least the rising part of the relation. Is that right?
Right. For the rising part of the relation, the relation between the normalized X-ray activity, X-ray Lx over L ball, versus the Rossby number is identical to plotting Lx over P. That is the point. This is not something I came up with. This was shown earlier in Pizzolato in 2003. So this is sort of, I mean, it's quite obvious. But of course, this does not tell you why you have the saturation for the rapid rotators. And then the point we made is, okay, physically, you might just think that there is a maximum average field strength or a total maximum in the X-ray luminosity that is proportional to the bolometric luminosity. There's an upper limit that is sort of universal. And if you combine these two things, then you can get away without using the Rossby number. But
Okay.
don't get me wrong. So what I was, so this is sort of an offering a different interpretation that I think, well, it might be an easier way or not, I don't know, but it allows us to show this plot without the uncertainty of the convective turnover time, right? So we were wondering what this really is, because if you all know that this concept of the turnover time for a thing like a thick convection zone is a bit ill-defined. And we try to, at least on the observational side, get away without it. And this is sort of what we tried, and it works. Whether that means that this sort of the ratio between rotation and convection has really no big influence, that is, of course, something that I cannot answer.
Okay, thank you.
Gustavo.
Ansgar, many thanks for the talk. I have a question regarding the observation of magnetic field with CDI, because when in these measurements show also this relation of magnetic field with rotation or magnetic field with Rossby number, but they also show changes in topology. For example, you can see a huge change in topology of the small or rapid rotators, N-dwarfs, compared, which are fully convective compared to the ones that are partially convective or the ones that develop a Tachocline. So it's puzzling to me why we don't see any change in the activity rotation diagram that you show when we see changes in topology in these CDI measurements. Do you have something to comment about that?
Yeah, as I said before, I'm always hesitating to interpret too much, or to try to interpret very much these topology maps, because yeah, they are not really providing an obvious picture, I think, right now. So if there was a clear picture somewhere, then I would probably start buying it. But at this point, I'm really a bit afraid that there's a lot of systematics that we don't understand. These systematics include the V sin I of the star, certainly, the spectrograph that you're using, so the amount of how well can you actually resolve the surface. And very, very important is the inclination of the star. So we have recently measured the surface field strength of AU-MIC. And in AU-MIC, the fortunate situation is that AU-MIC is really observed equator on. So it's an extremely symmetric situation. And it turns out that in Stokes V alone, so circular polarization alone, which is what most of the ZDI images use, you essentially see no dipole component at all. But if you use Stokes Q and U linear polarization, which is possible in this star because it's so bright, you actually see a very strong dipole component, 2 kilogauss. So we are missing a 2 kilogauss dipole component in the Stokes V image of AU-MIC.
I see.
And this can be explained by the high symmetry of what we see from AU-MIC, because it's really 90 degrees. The inclination is 90 degrees. We really see it equator on. This is not so strong in other stars, so we see more of the fields, and you can make an argument that you really get very good information from the stars, but how you can compare them and such, I don't know. So this is sort of my puzzle, and again, I'm not saying there's nothing to learn from it. On the contrary, I think we have to think harder and look at the sample and try to separate the systematics from the actual information, because as you say, there is a lot of information, and this is certainly telling us something. I don't know what at this point.
Okay, thank you.
Sasha, I'm going to let you have this last oral question.
Yeah, I have a question. Thank you very much for the interesting talk, and really, we already discussed distribution of magnetic field. But I have a question about what's important in terms of solar physics is to explain butterfly diagram. And Svetlana Berdugin already announced that was some observation butterfly diagram in other stars. And I wonder what the status of these. And it may be related to Tachocline because one of the theories of solar cycle predicts that butterfly diagram originates from Tachocline. So what can you say about it?
Yeah, there are a number of stars where these ZDI maps actually resemble something. So series of ZDI maps resemble something like a butterfly diagram. This is true. And I think if you do it that way, if you look at one star and you have a lot of observations from one instrument using the same methodology, this is certainly telling us a lot. So I think there are magnetic butterfly diagrams, at least a few in other stars, that really show something that resembles a butterfly diagram. Right. I don't think there has yet been any sort of clear scaling with sort of cycle period and rotation period so far. But as we get more of these observations, this will hopefully come out.
Thank you.
Okay, there are actually 3 more questions on the Jamboards. I think some of them you sort of addressed already. So I'm going to, in the sake of time, leave those there. Ansgar, if you're feeling energetic, no obligation, you're welcome to jump onto the Jamboard and answer them there if you want to. But I think we're going to move on to the next speaker. But thank you very much for an awesome talk. So thanks once again for staying up late at night on a Friday night and being here for us. We appreciate it.
Yeah, thanks for having me.
Okay, the next speaker is our very own Charles Baldner from Stanford, who's going to talk on more specific sun and Tachocline like observational things. Charles, are you ready to go?
I need just 1 minute. I'm going to have to share the presentation from a different computer, so I gotta.
Yeah, that's okay. That gives me a chance to say, everybody else, I encourage you right now, while it's still fresh in your head, to go to the Jamboard and write down what you think you learned from that talk about the overarching questions that we're looking for moving forward with the Tachocline. What are the next steps from the Tachocline? What did we learn from this great talk by Ansgar? What are the biggest takeaways? So if you have some energy, you jump onto the Jamboard and write down your thoughts there. Remember, there's no penalty for whatever you think. We're just trying to throw your wildest ideas out there. It's fine. Okay, you have a moment to do that while I know the Jamboards is a new idea for lots of people, but don't be afraid to use it. Just jump on there and write down your thoughts. Okay. We're seeing your screen, Joe.
See if I can make this full screen.
You get to go to slideshow in the middle of the, yeah, then it pops up to the left. Yeah, there you go.
Did that work? That did work.
Yay, off you go. Thanks, Charles.
Okay. So I'm going to talk a little bit about what we know empirically about the solar tachocline. So this is going to be a helioseismology talk because that's the only way we can directly observe, make any sort of empirical measurements about the tachocline, and that's how it was first discovered, of course. So I don't think I need to say a whole lot about what the tachocline is. I think we all know this, and we all know the basic structure of solar rotation. We have a differentially rotating convection zone, and then beneath that we have a radiative zone rotating as a solid body. And the tachocline is the region where differential rotation changes to solid body rotation. And this is a fairly narrow layer. And this is what it looks like. This is a rotation. This is a set of rotation inversions at different latitudes. Oh, I should have put the reference here. This is one of Sarboni's inversions. But you have fast rotation at the equator, slow rotation at the poles, and roughly constant rotation along lines of latitude until you get to the base of the convection zone, and then you get a narrow shear. And that's what we call the tachocline. So I want to start with just a little bit about what we have, what our observational data set is, which is of course helioseismic normal modes. And this is sort of important. Different modes which we can identify by radial order and degree L, have sensitivities to different parts of the solar interior. And I really like this plot from Rachel Howe's review in Living Reviews from about a decade ago, which shows roughly which modes sample which parts of the sun. And you can see we have all of the high degree modes give you sensitivity towards the surface. Low degree modes give you sensitivity in the interior, and then you have these wedges through the all-new diagram that sample different parts of the solar interior. And you've got this. Yeah, there's my cursor. You've got this narrow wedge right here, which gives you sensitivity to the tachocline. So those are the modes that we're looking at. One of the important things to note here is that they're relatively low degree, and that means that the wavelength is relatively long, which means that you don't get a whole lot of spatial resolution with these in the way that you do when you're looking at more high degree modes, or the modes we look at with local seismology. And this is going to be kind of a theme of what we know and what we don't know about the tachocline. We are really limited by the resolution that we can get. There just isn't as much information as we would like there to be. So this is just repeating what I've already said. It's the unresolved region at the base of the convection zone. One note that I want to make, and I do see this, I do see some confusion on this. I think we all sort of understand what the base of the convection zone is and what the tachocline is, but when you're talking about, or when you're looking at helioseismic papers, you're usually looking at one or the other. Either you're looking at a paper that studies the dynamics, that is to say the rotation of the solar interior, in which case you're talking about the tachocline, or you're looking at work that studies the thermal structure of the sun, which is the base of the convection zone. And these things are not the same thing, and it's although they are very nearly co-located, but they are the techniques we use are somewhat different, and the results we have suffer from different limitations and different systematic effects. Anyway, very quick history. So the first suggestions that there was a tachocline region at the base of the convection zone was in a series of papers in the late 80s. But the first real confirmation was Spiegel and Zahn in 1992. And that was also the first paper to use the word tachocline. And they were using, I'm actually blanking on what their data set was, but they suggested a model which looks, this was the structure that they proposed, and found that they could explain the frequency splittings that they were seeing with a model like this, which was a relatively narrow shear layer between the convection zone and the radiative zone beneath it. The problem, as I said, with studying the tachocline is that the modes that we have there just don't have sufficiently small wavelengths to actually resolve it, so that the shear itself is unresolved. One way to address that problem is to start with an assumed shape for the tachocline, or an assumed radial and, if you like, latitudinal distribution, and then try to model the splitting coefficients, and then use some sort of chi-squared or simulated annealing or something like that to see if you can get a best match for your assumed model. And a number of authors did this in the mid-90s, especially when data from Soho MDI came online. And this is a comparison of some of those early works. This was done by Sarbani, but she was using She was plotting her own results and Sasha's and Paul Charbonneau's. And you can see some differences. So there are differences depending on the model you use and the data set you use, but they're all relatively sharp rotation gradients. And this is a table of a number of those, the results I referred to, and then some subsequent work. And what you can see here is this is just a table of on the left, it's the position of the center of the tachocline, and the table, or the column rather, here is the inferred width. And you can see there's a fair amount of variation here, so especially in the width. So there's a fair degree of uncertainty. The one thing we can say with a reasonable amount of certainty is that the tachocline is located beneath the base of the convection zone. That is beneath where the adiabatic gradient goes from subadiabatic to very slightly superadiabatic. So that is fairly well established at 0.713 solar radii, and you can see all of these results have the shear layer beneath that. So the shear is in the radiative zone or in the overshoot layer.
Charles.
Yes.
So can you point exactly what you mean by this R in the figure that you presented before? Because not this one, perhaps the one by Sarbani.
Which one?
This one.
Ah.
So you exactly mean what transition here? Or what
sorry.
is this R? What is this R exactly?
R is this is just the depth of the inversion. So this, right. I'm not sure I understand what you're asking.
So because you need to define a point for the transition, and to define what kind of transition that is the one that you are looking, because different lines here have a different R perhaps, right?
Yes, so there are no model assumptions here for a tachocline. These are just inversions of rotation rate at different latitudes.
Right.
If we go forward, so if we look at this,
I think he's asking how are you defining what sets the range?
I'm sorry, I missed that.
So I think the question is, what does R mean? Is it the top of the tachocline, the bottom of the tachocline, the middle of the tachocline?
So for example, the R in this table here?
Yes.
Yeah.
So that is somewhat model dependent. But it's basically where the centroid of your of whatever shear model that you're assuming.
The center. Okay.
I mean, it depends on the form that you take, and these authors are all using slightly different models.
Mm-hmm. Okay, thanks. Sorry for interrupting.
No, thanks for the clarification, or thanks for insisting on the clarification. So this is a table from Rachel Howe's review again, and right, as I was saying, the assumed location is, whatever that means, is below the base of the convection zone, but the width is there's a fair amount of variation in the assumed width, and this is an even better demonstration of this. I got this from Sylvain. I'm not sure what the origin of this is, if this was published or if this is his own plot. But you can see here just he called it a smorgasbord of results, and this goes a little bit later than Rachel's table, I believe. But you can see again the position varies somewhat, and the width varies a fair amount. And then on the right side, the question is, what I haven't talked about yet is the shape of the tachocline. Does it have any variation in latitude? And there was a fair amount of uncertainty early on. Some of the first authors to study this did not find any variation in width or position with latitude. But now I think there have been a number of studies, in particular Basu and Antia and Basu from the last 10 years, that suggest that the shape of the tachocline is probably prolate, so it's a little thicker at high latitude than at the equator. But that's dynamics. I do want to talk a bit about the thermal structure of the convection zone and what we know about that. And that, it turns out, is actually significantly easier to localize very precisely. And that's because if you look at different models with different positions for the transition from radiative to convectively unstable, the difference in sound speed is actually quite significant. And so even though you don't have the resolution in helioseismic modes, the models that you use are actually sensitive enough to give you very precise a very precise location on the transition from convectively stable to convectively unstable. And the generally accepted value for the position of that transition is 0.713. And I think this was, I think that's been the accepted value for a couple decades now. And this is just an example from Sarbani's work of the difference in sound speed in the models on the left, and then the inversions that you can do using helioseismic data. So even though we don't have the resolution in the seismology, the models let us get around that. So then there's a question, does the position of the base of the convection zone change with solar activity or just with time? And this is, I'm just pointing out something that some dumb graduate student did about 14 years ago, suggesting that there might actually be some form of change at the base of the convection zone. These are on the right, these are sound speed inversions. And we found that we might be able, that we found a little change that was very tightly correlated with solar activity that we could interpret as a change in the sound speed. And we could also do that as a function of latitude. This is not the sound speed directly, this is the linear coefficients that we fit. But you can see that it does seem to track with surface magnetic activity quite tightly. This is somewhat more recent work, actually a lot more recent work. Sarbani has gone back to this and finds, and this is a rather than a direct measure of the sound speed, this is a measure of the gradient at the base of the convection zone. And on the left, it's just plotted as a function of time and whether or not you, it's not easy to pick out any solar cycle related change there, but there is a very small trend that seems to depend on surface activity. So the evidence is there that there may be changes, but they are very, very small and very difficult to tease out of the signal to noise. One question one can ask is, are these changes, are there changes in magnetic field at the base of the convection zone? And this is work I did a while ago. This is a forward model of a toroidal magnetic field seated at the base of the convection zone with different widths. And this is a field with plasma beta of 10 to the -4, if I remember right, which comes out to something on the order of a megagauss, I believe, at the base of the convection zone. So it's a strong magnetic field. And this is just these are the effects on the splitting coefficients. So this is the effect that a seated magnetic field would have in lifting the degeneracy on modes that penetrate the base of the convection zone. So it takes a very strong field even to make a very small effect on the observed helioseismic frequencies at the base of the convection zone. So in principle, yes, there could be magnetic changes in magnetic fields there could be detectable, but in practice, it's difficult to see how we could get fields strong enough to actually to exceed the signal to noise in these modes. But that is that is something that in principle we could do. So let's go back to rotation and to the Tachocline, going to time variation now. This is work that Sarvani and Antia have been doing, and these show changes in the rotation rate at the base of the convection zone at different latitudes. That's on the left, and you can see that that there is time variation across several solar cycles. And on the right, they're plotted as a function of solar activity. And you can see that there does appear to be some degree of hysteresis. So the cycles don't behave the same on the rising and falling phases of each cycle. The problem is that there are some fairly significant systematic effects. So this is an example of the position that you infer for the tachocline, and again that depends on the functional form that they assume, and I can't remember off the top of my head what that is. But you can see, so the blue and cyan are the space-based measurements from SOHO MDI and then SDO HMI, and the red ones are GONG, and you can see that there is a systematic offset that's statistically significant. So systematic effects here are playing a role, which is maybe not surprising if you've been looking at helioseismic results for any significant amount of time. But that is a problem that will need to be addressed. Oh, well, I'm going a little faster than I meant to. The existence of the tachocline is empirically well established. We know roughly where it is and the relation it has in depth to the base of the convection zone. We believe that it's prolate in shape, although that's somewhat less certain, and the width is fairly data and model and analysis technique dependent, so there is still work to do there. Systematic effects do matter, as they tend to anytime you try to get to relatively small signals in helioseismology. Both systematics in the techniques and also in the data sets seem to matter. The basic challenges that we face in studying the tachocline, that is studying the dynamics, is the limited resolution that we have. The resolution in depth is not enough to resolve the width of the shear. So we're stuck using models and trying to look for effects that way. In thermal structure, there are ways around the resolution issue, but the issue there is that the changes are so small that signal to noise is the major issue. One way that some people have been trying to address this issue is by using longer time sets. So we now have year to year, even whole solar cycle long data sets that have been analyzed and fit. But then you have the problem, in addition to any systematic effects from, say, secular trends in instrument performance, you have the issue that any variation is being smeared out and is increasing your systematic errors. So I think I will leave it here. I'm sorry I went, that was a little shorter than I meant it to be, but I've been rather distracted this week. And I think I will take questions or criticisms.
No worries, great. Plenty of time for discussion. Thanks very much, Charles. Questions? I see a hand up from Brad. There's a bunch of things in the Jamboard I'll look at, but there's a hand up from Brad, so let's let Brad go.
Thanks, Charles. I just wanted to ask a question of clarification. You made the point that the base of the convection zone is above the tachocline, but if you, yes, the center of the tachocline by some sense, but the tachocline as we can measure it has some width.
Yes.
Does the base of the convection zone fall within that width?
Yes, it does. I'm sorry, I should have said that. So you can see, I mean, it depends on the work. But if you look, for example, if we start with Sasha's result from 96 here, you can see a width of 0.69, or sorry, a location of 0.69 and a width of 0.09. So that does put the, you do get a shear extending up into the, up past 0.713. And I think that's common with most of these, that the width is enough. Yeah, I should have been more clear about that. Thanks.
Okay, and one final question from me. You mentioned that there's some evidence that the tachocline is prolate. What is the variation in width roughly from equator to pole? You may have said this and I just missed it.
I did not say it, and I don't know the number off the top of my head. Though someone else here might. I'd have to pull Sarbani's paper up.
Sylvain, do you know offhand as well?
Not on top of my head, but I want to make a small comment since you asked me. You know, all those widths are upper limits. I don't think we have any way of putting a lower limit on the width of the tachocline, you know. And if you go back to the plot that Charles showed, you know, there is sort of a tendency with time to find that the width is more narrow as you get better data, and then you jump with other data. So, you know, we have to be very careful about what is the measured width, because of course we have limited resolution there. So we really only have a upper limit. I think we have a lower limit to say that we know. So it could be very narrow, it could be below, it could be indeed extending above. And I'll try to pull the thing from Sarbani to answer the other question.
I agree with that mostly, although a number of these results are some form of a best fit. So they actually do reject small widths as well as large widths. But I think in general, yes, the main thing we can say is the width of the tachocline is smaller than a given upper limit.
And Charles, and this is an argument I have, you know, with Sarbani, who is not here, is that you cannot think that the forward approach doesn't have an implicit, you know, limit in resolution. If with inversion, you know that the beauty of the inversion is that you can measure your averaging kernel, so you know by how much you're smoothing the real underlying, you know, shape. The forward model give you a statistical best fit, but doesn't give you, doing the forward analysis doesn't give you more spatial resolution at the depth of the tachocline.
I agree with that, but it does. There is subgrid scale information in helioseismic mode frequencies that a forward model can help you tease out.
Which brings me up to a question that I was just putting onto the Jamboard. If the tachocline really was just a jump, there was an actual discontinuity, shouldn't that spread be obvious in the data in some way? Is there a way of getting an idea of a minimum width by doing something like that? This is effectively how you can measure the depth of the bottom of the convection zone so accurately, is because it's such a sharp discontinuity.
Well, the issue with the the way you measure the base of the convection zone is that there's effectively a cumulative effect in sound speed as you integrate further down. There's no equivalent to that in dynamics. Douglas Goff, I think it was Goff who did a I can't remember which paper it was, actually tried to use a discontinuity, allow a discontinuity in the inversion and see what they could do. But I don't know how tightly that lets you put a lower limit on the width.
Charles, if I can jump in, I've also tried that with Felgoody and Jambowski back when, and the reality is that it's not actually stable. If you do an inversion, you cannot allow for discontinuity. It's just numerically unstable. So those results need to be taken, with a grain of salt.
Okay, thanks.
Thank you, Sylvain.
Yeah, Lauren's been waiting patiently. Lauren, go ahead.
Well, thanks. That was a nice talk. I had a question about the Tachocline widths. It seemed like there was kind of an extreme distribution. There was one value like around 1% and one value around 10%. Could you comment on that? I mean, what's going on at the kind of tail of that distribution?
Well, the fundamental issue is just that we're trying to measure a quantity that we don't have the information to measure. is what this we don't the width of the averaging kernels that you can get in an inversion are larger than the Tachocline. So the distribution that you're seeing is a distribution in technique, in methods, in assumed models, rather than anything in the data itself, I think.
Okay. Okay, thanks.
And the other thing that when you're looking at this plot, the other thing, and Sylvain mentioned this, but it's something to bear in mind when you're out at the when you're looking at results from earlier periods, you're looking at different data sets than the sort of the high duty cycle, long time baseline space-based sets we have now.
Okay. Is there like a more settled recent value, or do we really think it could be kind of anywhere between 1% and 10%?
I suspect that most of us would say it's probably closer to 1% than to 10%. But no, it is still an uncertain value. Okay. Again, because the issue is the resolution just isn't there.
All right, thank you.
Amy, I see your hand up.
Hi, good morning. Yeah, I had a question. You showed some data that the results might be dependent with the amount of activity, and I can't really visualize what that would look like. I mean, is this just can you tell us what that might look like in terms of what's physically happening?
So do you mean the thermal changes or the dynamical changes?
I don't know what you mean by the difference.
So there are two different sets of measurements. One is the thermal structure, and that's what I'm showing here. And then the other is the rotation rate change. The rotation rate change, I think, is fairly easy to visualize. It's just, I mean, we know that the convection zone speeds up and slows down with solar activity.
Okay.
So it's not surprising that the shear layer does as well.
Okay, so what is the plot before this one? There was another one that you were discussing. One more. That one.
This one?
Yes.
So if you believe this inversion and this analysis, what this is saying is that there is an increase in sound speed right at the position of the base of the convection zone, and then a decrease below it. And that change is very tightly correlated with surface activity. That's this panel here. In terms of what that means physically, does that mean that there is a slight shift in the base of the convection zone, or that there is some kind of thermal perturbation, or what? That I don't know.
Okay, so it could have several interpretations.
Yes. And it could also be, there's also the possibility that this is contamination from the surface, which is kind of the major. I said signal to noise was an issue. The other major problem is that almost all of the variation in helioseismic frequencies that you see are due to changes very near the surface. So anytime you're doing work deeper down, you are looking for signal that's just a small fraction of the total variation. So one always has to be cautious.
That's
All right, thank you.
Just to jump in quickly, that's also correlation with the surface magnetic field as well. It doesn't say anything about the magnetic field at the location of the base of the convection zone, right?
Correct.
So there's all kinds of confusing issues there. But anyway, Sylvain, you have your hand up.
Yeah, and you just introduced exactly what I would say. If Charles goes back to a Rachel plot about where the Tachocline is sensitive on the modes, you have to remember, which is exactly what you were saying, that essentially is the inner turning point. All those modes bounce at the surface. So if you want to measure something as deep as the Tachocline, you need to essentially subtract the effect of everything that is above. And if you don't do that right, and we see change at the surface, like, because of magnetic field and things like that, you will inject them further down. And so it is important to have all the modes possible with the best possible precision, because you're essentially doing a differential measurement every time you go anywhere below the surface. So that's sort of, the other thing, if we go back to the definition of the depth of the Tachocline, it's very model dependent. And that's why I said my guess is roughly where is the inflection point of the profile that is assumed in the modeling. But what has been missing a lot in the measuring, historically in the measuring of the width, is to well-established error bars. And if you go back to that plot, not only you can see a trend in the measured width as a function of time, but a trend with the error bars. So eventually people have been a lot more careful and tried to get very small error bars. And to answer the question before, there was about the width variation with the latitude. Let me share my screen if I may. Charles, I want to show 2 slides. Let me try first this one. And so this is what Sarbani presented when Sarbani and I gave a talk a while back. And if you look in this panel, that was an old estimate of the change of the width with latitude. And Sarbani sent us a different plot that Charles didn't have time to include. And I will show this one, which is a more recent analysis. So there are a couple of differences. First, she's using a 3-year-long, time series that, that I fitted. So those are modes that I produce, and you can see the change equator 15, 30, 45, or 60 degrees. She's using a different forwarding method, which uses a more drastic analysis. And the different colors are for time series that starts at different dates. And if you can convert the MDI mission number into a date, but the point is that there's very little change of that dependence of the width with latitude as a function of time. And she's getting here tighter, probability distribution of what the width is by using longer time series. Thanks.
Sylvain, for this figure, what is the center of the Tachocline for this analysis, this new analysis?
This is Sarbani, work, and I have tried to see. I'm not sure that it is in what she sent us. So I'm sorry, but I have to punt that question.
Mm-hmm.
She does have a different plot for the radius. It's obviously not that I didn't have time to do it. I just wasn't confident enough I didn't understand it well enough. I didn't want to risk.
Charles, sorry, this is nothing personal. I hope you know that. And I think that Sarbani did a full new analysis using new data and a more robust method, but this is, I think, still work in progress. And I wish she was here to show you that. I think she flashed it at some other talk we had, maybe, which is the rotation inversion group we're working on. So
we had a question from Peter Gilman in the chat. Peter asked, is there any hope to measure Rossby waves in the tachocline?
Hope, yes. Expectation, no, I think is probably the best answer. It's there. The signal to noise is fairly low, even at shallower depths.
But yeah, Charles, if I can step in, that's the really issue, is really the precision of the observation to be able to infer something that, you know, we've detected no Rossby wave, but the precision on their period or frequency,
yeah,
is not at all comparable to what we have with P modes.
One thing to point out, the Rossby waves that have the work that's been done to detect Rossby waves uses local seismic techniques, which have much greater temporal resolution. So you can do 8 hours or 24 hours, whereas everything here is a minimum of 72 days. And actually a lot of this stuff is using 360 or more.
Well, even if you didn't get the spatial distribution, can you in any way detect the phase velocity of a Rossby wave? Like wave number 1 would be retrograde almost certainly and pretty fast. Can you take advantage of anything like that to find it?
I wouldn't want to do it using these data sets. I would want to use some form of deep focus, local time distance or something like that. I don't know if Sylvain disagrees with me on this, but I think given that you're looking at multi-month long temporal resolution.
Yeah.
But you also run into the problem that to measure the Rossby wave, you probably need to have longitudinal sensitivity in the measurements, which these global mode measurements don't have.
Yeah.
Oh, that's a good point. Yeah.
And if I can jump into the question before, I did find the slide from Sarbani about position. So I'll just share that slide if you don't mind. So this is, similar, so I showed you this one, which is the distribution of the more likely position of, more likely width. And this is the distribution of the position. And again, as a function of different latitudes, and with colors as a function of different time series. And there, of course, you see her question, are those changes real? Since we know that there remains some systematics in the mode fitting.
There's a couple of other questions on the Jamboard which are related to this sort of stuff, and I think you touched on it a little bit, but let's just see if it brings up anything else. So there's one question says, what does it mean strong enough field to be detectable? 10 to the 4, 10 to the 5 Gauss. So I think this again goes to your signal to noise. So you can say that there are small, I think you already said that strong field variations are potentially detectable, but then there's a signal to noise issue. Do you want to comment on this, or is it just what you said before?
Well, it depends on, it's not just the strength, but the width and the depth, and it's strongly depth dependent. So if you're talking about the base of the convection zone, a toroidal field with plasma beta of something like 10 to the -4 is detectable. It's been a long time since I've tried to place upper limits on that. That's a thing I should go back and do now that we have more than a solar cycle's worth of HMI.
But Charles, if I can step in, because there was a question related. So the nice thing about rotation, if you do, is that the rotation makes a frequency shift that is antisymmetric. The magnetic field will do a frequency split that is symmetric, but it's not the only one. You can also have a change, in sound speed structure that will give you changes. So there is no uniqueness between the change of the symmetric part of the frequency splitting and the cause of it. So that's also what is, dangerous about, assuming that the changes are only due to the magnetic field. And of course, you can say, well, if you put a magnetic field, you will change the structure in any case. And so how do you disentangle the two, which has been also a problem when you do local heliosysmology, around, and below sunspots.
That's a more significant problem in the shallow layers, where you're getting much closer to beta of unity.
And I think, Sylvain, you just addressed one of the questions that's on the Jamboard, but there's another one that just asks sort of the obvious question, would improved inversions and kernels help with the signal to noise problem? So is there anything we can do about the signal to noise problem?
I don't think that the kernels will change anything in the signal to noise ratio. We do have a bit of a problem, is that we don't have a perfect solar model. You need a solar model to compute your rotation, to compute any kernels. And the interesting thing is that when we did the big simulation, is that I historically used Roger's solar model and not Jürgen Künzel-Soldasgaard, S model to compute my rotation kernels. And when you invert a perfect simulation, you see a difference at the level of a few nanohertz. And that brings the question that neither of those is the actual sun. So we may have some systematics, even in results of inversion. But essentially, the kernels are very well known, unless you go very close to the surface, where we have primes, because of course the surface is not uniform, and we're essentially using, the assumption of a radial kernel. But otherwise, the kernel can be very well computed if you know the profile, but we don't know at the level of precision we're trying to push everything, the actual certification of the sun.
Okay, thanks. Shay, you had a question.
What Sylvain said. So the surface is much more complicated, and well, I mean, I don't know. I think things are complicated in different ways, but I guess my understanding of the Tachocline isn't strong enough, because it just seems like there would be different complications. I mean, the surface mixes things up and messes things up more, but I mean, the Tachocline is still a shear layer, so won't those complications have to be taken into account in any of the physics involved in the inversions? I mean, you say the kernels are really well known for the deeper layers, but how do we know that, I guess, is my question.
I think the base of the convection zone and the Tachocline probably are significantly simpler than the near surface shear layer, and where the convection becomes fairly strongly super adiabatic. I think the convection is smoother, is slower and smoother, and you don't have, and even if there are magnetic fields, they're very small compared to the gas density. So I think the properties at the base of the convection zone, or the structure of the sun is simpler there than it is at the surface. In terms of how well we know the kernels, though, I mean, that's a hard question to answer. We know that we can predict solar frequencies pretty accurately, and we know that most of the errors in our predicted frequencies arise from uncertainties in the kernels at the surface rather than at the base of the convection zone. So in that sense, we know them much better there than we do at the surface.
Go ahead, Sylvain, if you want to say something.
Yeah, but that's why I just want to disagree for the fun of it with Charles. Is I tend to see the glass half empty and not half full. All the modes, go all the way to the surface. And we have always, to be very worried of what's happening at the surface. Once we push the data, to the highest precision we can get. And that's where, we have the answer roughly right, but once we push it to be, to see minute changes, are we sure that by using an adiabatic model, and we know that the surface, the layer close to the surface is not, and we know that the surface is not as simple as we'd like to think, how does that affect, or inferences.
Okay, I just want to make a couple of comments myself, and then I want to give people time to grab some coffee and take a little break before we start Peter's talk at 11, so everyone gets a little bit of a moment to stretch their legs, get some coffee. But my comments are just, well, a couple of things. When you do simulations of multi-layer systems, so a convecting layer sitting on top of a radiative layer, so you do overshooting convection, then a lot of times when you get overshooting convection, the point where convection mixes things to be adiabatic retreats a little bit. So the base of the convection zone, if you measured it just by what is adiabatic, sort of shrinks up a little bit. So I think this is an interesting effect. It actually has a name, and I forgot what it's called, this effect, but I think that's an interesting point, because a lot of so from a theoretical point of view, a lot of times what you want to know is what are the dynamics of particular layers. And so, you know, there's still convective like stuff going on below what might be the actual, what's called the base of the convection zone by just thermal measures. And we've always known that because we've always assumed there was some sort of overshooting, but actually sometimes there's more than just overshooting. There's a little bit of the base of the convection zone too. So that's one point. And I'd love for the theoretical modelers to discuss this later on or comment on that one. And the other point is, you know, again, a sort of deeper thought in a way, to try and distinguish between theoretical and dynamical theories for the tachocline, we kind of need to know sub layers of what's going on in the tachocline, whether there's a region that which is field free, you know, where does the overshooting stop compared to, you know, this R, the center of the tachocline, etc. It would be lovely to sort of know these things. I mean, do we ever have any hope of distinguishing between these theories by knowing what's happening in sublayers of the tachocline? Anyway, those are questions I want to just throw out there for everyone to think about. It's 10:49 to suggest we take 10 minutes break, stretch your legs, do whatever you need to do, grab some coffee, and then we'll come back for Peter Gilman will be telling us about tachocline instabilities starting at 11. Peter, if you want to start getting yourself set up, you can do. I'll be back in 2 minutes. All right, everyone, see you in 10 minutes. Oh, and thank you, Charles, once again. Thank you for the talk.
Thanks for the invitation.
Okay, I'm back. Peter, you want to try sharing your screen? Make sure everything's working. You're muted right now. Now is the time you can unmute.
Okay, now I'm unmuted.
You're unmuted now.
Can you see my first slide?
No, you need to do the share screen thing. So press the green button down the bottom, the share screen one.
Yeah, you know, what I've got to do, I've got to go behind this thing. Whoop. This is really strange.
If you press that green share screen button, it should bring up a
Yeah, I got it.
choice of which screen you want to share.
Yep.
There you go. Now we're starting to see something. Yeah, there we go.
Yeah, it's working.
Now you hit your slideshow from the beginning. Top left.
Right.
Yeah, there you go. That makes it full screen.
All set?
Set. Yeah.
Another couple of minutes to return and then.
Wait a minute. Hang on. How do I advance my slides? It disappeared.
You should just be able to click on it, I think. If you click on the slide.
Oh, yeah. Okay. And I go backwards, how?
Just use the backwards arrow, I think. The arrows work as well.
Where are the backwards? I can't see anything. It's full
On your
screen.
keyboard.
In your keyboard.
Oh, that's right. Okay.
Peter, use your keyboard to navigate. Forget your mouse.
Got it. Okay.
All right, let me.
Sorry for the clumsiness.
Oh, no worries. Let me just wait one more minute for people to come back, and then I'll give you a quick introduction, and then off we go.
Okay.
Can't actually tell whether people are back or not. All right, it's officially 11, so let's get going. Our next speaker is Peter Gilman from HAO. We're very lucky to have Peter here. Peter is someone who's essentially spent a lifetime working on the Tachocline, which is very impressive. Although there was a period where you were severely distracted by administrative duties for HAO, if I remember rightly. So,
And NCAR.
Yeah, we regret that time while you were director. But anyway, so we're lucky to have Peter here, and he's going to tell us all about the possibility of instabilities causing turbulence in the Tachocline. So Peter, take it away.
Thank you. Okay, so I thought I'd try to give an overview starting from basically instabilities arise when you have reservoirs of energy that can be tapped by perturbations. And in the case of the Tachocline, there's at least 6 that I listed here, namely the latitudinal differential rotation, a latitude thickness variation, you have potential energy involved, a vertical differential rotation, latitude specific entropy gradient, latitude toroidal field gradient, and vertical toroidal field gradient. Each one of these gradients provides an energy source, basically, and you get different instabilities out of different energies, right? And you can get combinations of these. So, in terms of known instabilities, latitudinal differential rotation alone gives you what the meteorologists call barotropic or vorticity inflection point instability. If you add make it into a shallow water model where gravity comes in, then you get inflection point, but of the potential vorticity, which is the ordinary vorticity divided by the thickness. Then if you go to latitudinal differential rotation and latitude toroidal field gradient, then you can get joint instability of the differential rotation and the toroidal field. And I'll spend a fair amount of time on that one. Well, the vertical differential rotation and latitude specific entropy gradient leads to what's usually called a thermal wind in the Tachocline, and that would lead to baroclinic instability, which is transporting heat from from warm latitudes to cold latitudes. If you then add a toroidal field to the baroclinic instability problem, you get baroclinic instability modified by toroidal field. If you do latitudinal and vertical differential rotation and toroidal field gradient together, you get a more complicated situation, which has never been cracked as far as I know. Now, combinations of energy reservoirs. This is now, those previous ones were all global scale disturbances, but you can also get disturbances on small latitudinal scale. So if you have a vertical differential rotation, but no thermal wind, you can get rotational instability from that. A vertical toroidal field gradient in small latitude scale, you can get magnetic buoyancy instability from that. You add rotation and you can modify the magnetic buoyancy influenced by rotation. If you have vertical differential field and toroidal field differential rotation, is a mistake there, and toroidal field gradients but no thermal wind, then you get to bulbous Hawley or magnetic buoyancy and rotational instability, all those. Now, the mechanism by which the energy is released from these reservoirs is stresses, basically. The classical Reynolds stress correlation between perpendicular velocity components, that acts on differential rotation. You can get Maxwell stresses when you have a magnetic field present, that also acts on differential rotation. And you get what we call mixed stresses, which are correlations between the perpendicular velocities and magnetic fields. And those act on the toroidal magnetic field to extract energy out of it. You can also get thickness transports. If you have a shallow water model, for example, and the thickness varies with latitude, if you can transport the mass around, you can get some potential energy out of that. Thermal stresses, which would be a correlation between latitudinal velocities and perturbation-specific entropy, acts on the latitude-specific entropy gradient to extract energy. And finally, vertical density transport, a correlation between the perturbation vertical motion and perturbation density, acts on the density stratification of the layer. So you could go a little bit further into what these stresses look like. Reynolds stresses and Maxwell stresses, if you look at the disturbances, what you will see are tilted velocity streamlines. And the sense of tilt determines the direction of angular minimum transport, either up or down the gradient. Same thing with Maxwell stresses. You get a tilt there as well. Now, if the sign of the tilt in Reynolds stress and Maxwell stress is the same, then these two stresses oppose each other, and that makes a very interesting combination. And finally, with the mixed stresses between magnetic field and velocity field, that's not a tilt, that's a longitudinal phase difference between the velocity streamlines and the magnetic field lines. The thermal stresses, that implies a longitudinal phase difference between velocity streamlines and specific entropy perturbations, and the vertical density transport, by analogy, longitudinal phase difference between the vertical velocity and density perturbations. Now, how are these energy reservoirs refilled? If you have an instability growing on it, you're going to take energy out of it. Well, two obvious ones. The differential rotation energy in the tachocline is surely resupplied from the convection zone above. Very fast processes there that are reestablishing the latitude gradient, basically. And then toroidal fields in some way are resupplied by the solar dynamo. Now, you make different assumptions depending on how many degrees of freedom you're allowing in the models. So in the 2D case, there are really no additional assumptions. With shallow water, now you have a deformable top, and you have hydrostatics. And 3D, of course, you're assuming hydrostatics in the reference state. In the equilibrium state in latitude, you're generally having a balance among the Coriolis force from differential rotation, the magnetic forces from the toroidal field, and a pressure gradient force or a height gradient in the shallow water case. And in the shallow water case, it's a particularly interesting thing. You can have a prograde jet inside the toroidal field band or a retrograde jet, and then you get a modified force balance, which is still a force balance. I'll come back to that a little bit later. Now, for vertical differential rotation and toroidal field variations, you're still talking about hydrostatics in 3D channels. Typically, it's hydrostatic and so-called geostrophic flow, which is the case when you have perturbation pressure gradients and Coriolis forces balancing. In 3D spherical shells, hydrostatics, but generally non-geostrophic. You don't have that for it. And that's very important because then you can get to the equator. In equilibrium state and latitude, the Coriolis pressure gradient and magnetic forces balance. In the vertical, it's these forces, of course, plus gravity. Now, for small latitudinal scale, the vertical differential rotation and toroidal field variations, we assume infinite radiative diffusivity. Otherwise, it's an ideal fluid. And this eliminates a very common instability in meteorology, Kelvin-Helmholtz instability, the so-called Richardson criterion, where if the shear is large enough, you'll become unstable. And that's an important point I'll come back to towards the end. In latitude, the Coriolis pressure gradient and magnetic forces balance, and the vertical these forces plus gravity balance. Now, there's some parameters you're going to see in some slides here. Now, I'm not going to give all the details of them, but the capital G is the effective gravity. That comes in for shallow water models and anything 3D. There's a magnetic Richardson number, which is like an ordinary Richardson number, where instead of the subadiabatic stratification, you put in a toroidal field strength. And you're going to see a parameter A, which is a dimensionless measure of the toroidal field. And just keep in mind that an A of 0.1, it's a toroidal field of 10 kilogauss. But we're actually going to talk about field strengths for various instabilities. And then H in here is a sort of mean square wave number, both longitude and latitude. That applies mostly to channels. And then M is a longitudinal wave number in spherical geometry. And that's the usual spherical geometry parameter. It's always an integer. So now just some general properties of instabilities in the global realm, the low longitudinal wave numbers M are usually the most unstable. If it's rotating, then all unstable loads have some characteristics of Rossby waves, particularly their longitudinal propagation, but they're not simple Rossby waves. If you omit the latitude variation of the Coriolis parameter, then you get no Rossby waves. But you still can get instability. They're just less realistic for spherical shells. In the MHD case, you're generally going to have alpha waves present, but they're generally not unstable. It's really the shear of one sort or another that's giving you the instability. For instabilities local in latitude, we're going to learn that both low and very high longitude wind numbers can be unstable due to different mechanisms. In the pure HD, rotational instability has growth rates and longitude speeds that are independent of M, in fact, so they're all unstable. So to talk specifically about global tachocline instability, this is now 2D hydrodynamic, well known for decades that 2D HD instability in spherical shells requires an inflection point in the latitude differential rotation profile. That's the place where the latitude vorticity gradient of the differential rotation changes. Now, Watson tried to apply this to the sun and used a very simple form for the differential rotation, which only had the sine square latitude term in it. And he concluded that it was stable unless the differential rotation was close to 0.29, which is about roughly what it is at the surface. And he postulated the sun operates at this stability limits. At that time, the tachocline was not known. Now, Zimbowski and Kozavichev looked at this again and took a profile that had the sine's fourth term in it. And that turns out to be crucial for instability at smaller differential rotations because the inflection point changes. So Watson's hypothesis for why the sun's differential rotation is limited the way it is not valid. Now, Charbonneau, Ducati, and myself extended their result, but determined that in 2D systems, the observed solar tachocline is actually stable to this kind of perturbations. Now, in this case, of course, in all cases, the unstable disturbances are drawing their kinetic energy from the differential rotation via latitudinal Reynolds stresses. Now, this is the first time when we added toroidal fields to the differential rotation. Gilman and Fox, 1997. We used the old sine square profile, and it doesn't really matter in this case because as soon as you add a toroidal field, you get instability for much lower differential rotations. This, two plots of the growth rates. A growth rate of 0.01, by the way, has an e-folding growth time of about a year. So you can see you can get down to very low differential rotations here And you have two kinds of modes, so-called anti-symmetric and symmetric. These are just the opposite symmetries of all the variables. Longitude, the latitude motions and all the other motion and latitude magnetic fields have the opposite symmetry about the equator from all the other variables and vice versa. So it's unstable, but this is all for just wave number one. That's the only one that's unstable for a very broad toroidal field profile, which is what this was, just anti-symmetric about the equator. Now, if you get into the energetics of this instability, you can produce an energy diagram like this. And what's happening in this instability is that the Maxwell stress now is taking energy out of the kinetic, out of the differential rotation kinetic energy and putting it into perturbations. Whereas the Reynolds stress is actually trying to reestablish the differential rotation. If the field strength is high enough, then you're going to get most of your energy out of the magnetic field, and the differential rotation is acting more like a catalyst to get it to come out. Now, it gets more interesting when you start looking at other profiles. The solid curve there is the original profile. And then assuming Ducati and I worked on much narrower profiles, which is probably more realistic for what's happening in the tachocline. And the instability changes as you increase the narrowness. So this is a plot of some results with what you see plotted here is the bandwidth at the bottom. So very narrow bands on the right, very broad bands on the left. You can see, for example, particularly for narrower bands, you're getting higher wave numbers, which is 1, 2, 3, and 4. So these are cases where the toroidal field is not tipping, it's deforming. So these are all happen to be at 10 kilogauss. And you can go up to very high toroidal field strengths. In fact, wave number 1 can be unstable almost up to almost any field strength. That's now, just to show you what a typical unstable disturbance looks like there on the right, as the bandwidth shrinks, all the magnetic perturbations are all in the shading, and the velocity perturbations are the contours. You can see as you go from top to bottom, you're getting great concentration of the magnetic perturbation. No surprise, because that's where the toroidal field is, but you're getting almost neutral velocity perturbations away from the band. So all the actions right inside that band, where in fact the tilts occur and the very sharp phase changes between velocity and magnetic fields as a function of latitude. Now this is a plot that shows you within each of these, just for again for a whole range of bandwidths, what the Reynolds stress and Maxwell stress look like, and you can see, generally speaking, the Reynolds stress is opposing the Maxwell stress. The net has to be positive so you can extract energy out of the differential rotation. And if you look closely, you can see these vertical tick marks on these plots. Those are so-called turning points of the system where the basically the rotationally shifted phase velocity is equal to the alphane speed at that point. And that's where almost all the action is mathematically and physically. And if you really want to go into the details, I won't drag you through this whole table, but you can actually work out analytically all the stresses in the system in terms of the phase shifts and the tilts of velocity. This is a lovely set of diagrams. You can use them for diagnostics very well. Now, what are the initial sort of nonlinear consequences of this instability? These are names which Paul Cayley invented. If you have a very broad toroidal field, you see the plot on the right here. What happens is, as the instability grows, these very broad toroidal fields start to tip, and it opens up in one hemisphere. That's why he called it clamshell instability. If the band is narrow, you look down the lower left, what you get is that the band wobbles. You can get deformations if the field's not too strong, but if the field is strong, then all you get is wave number 1. And what's happening here is the band is acting like a gyroscope. That is to say, just think of it as a gyroscope. We'll come back to this in a minute. It doesn't like to be, it'll be tipped, but if you have to bend the band, then there's a lot of work being done against that to prevent it. So now going to the shallow water case, Now the top surface is allowed to deform and gravity is explicit. This table, this diagram on the lower left shows you the range of this parameter G as a function of the thickness of the tachocline and the degree of subadditivity. You can see your range. So in some sense, the radius of tachocline is on the left in that diagram, and the overshoot tachocline is on the right. So, and we can do all these cases. And you can see that the thickness that we chose was a range which is similar to what we saw in one of the previous talks. Now, the force balance and latitude now involve deformation of the top surface, and it can get pretty extreme if the effective gravity is relatively low. You can actually split this tachocline into two parts, an equatorial zone and a polar zone. So you have to watch out for that. Now you're getting a new energy diagram. This is back to the hydrodynamic case, and now you're going to have meridional circulation coming in. The 2D case, you can't have any meridional circulation because there's no place for the mass to go. But since you have a deforming top surface, you can get some meridional circulation in this. And you also have potential energy from the shape of the free surface. As it happens, we don't see a lot of action from the potential energy, but it is there and can, in principle, participate. Now, if you look at the typical growth rates of the instability, now as a function of this effective gravity parameter. So again, the overshoot, the rate of tachocline is on the left, and the overshoot tachocline is on the right. So you can see the instability, and of course the rate of tachocline is essentially equivalent to 2D because nothing deforms very much. But you can see kind of two regimes of instability depending on what that gravity parameter G is. And in general, you can get more instability at lower G. And if you make a regime diagram for all this in the tachocline, what you end up with is that the differential rotation as it is observed is unstable to shallow water disturbances at considerably lower total differential rotation than at lower effective gravity than when the effective gravity is high. And this extends, if you look on the right diagram, you see the unstable region extending into towards the top of the radiative zone. So that makes, in effect, says that the tachocline should be unstable to this kind of instability. Now you add magnetic field to this, and it gets even more complicated. And this is where this jet idea comes in. Some of you may know about something called polar slip instability, which is if you just put a toroidal ring in a band in the tachocline, there will be a tendency for it to slip towards the pole because there's a stress in that ring which is trying to contract it. Well, you can counterbalance that if you put a jet inside the ring and make it go faster, and then you can get a new force balance with a jet inside of it. So, and we don't actually know whether there's any jet inside, but there's a tendency for these rings to slip towards the poles. So one way to keep them from doing that is to have the angular velocity be higher inside. So now you're still getting the unstable modes now, and the difference between the no jet case and the jet case is really all in wave number one. You can again think of this as a gyroscope. That is to say, in wave number one, you have this spinning thing like the spinning top, and it doesn't like to tip its axis at all. So that it's unstable. Whereas for the higher modes, the m equals 2, m equals 3, there isn't a whole lot of difference whether the jet or there isn't a jet. And you can build regime diagrams for this also. The horizontal axis here is this toroidal field strength. So this is going, the top is from 100 Gauss up to 10 to the 6 Gauss. And you can see you get instability at reasonably fast growth rates almost everywhere, particularly if the toroidal field strength is less than, say, 10 to the 5th Gauss. So it's going to be very common in the shallow water system. Now I want to shift gears to a different instability, the so-called baroclinic instability in the toroidal field. This actually goes back, I couldn't resist doing this. It goes back to my PhD thesis, which is, what, 56 years ago. So now this is a very nice diagram because it illustrates how the Rossby waves and the Alfvén waves and the instability all play a role. So the assumptions in this simple model, now we're talking about a mid-latitude channel, thermal wind only, no latitude differential rotation, a uniform toroidal field, Coriolis parameter constant in the channel in this first plot at least, and the perturbations are geostrophic. So here, the perturbations themselves, the balance horizontal pressure gradients with Coriolis forces. Now the graph here, this vertical is this magnetic Richardson number. So the higher is P, the stronger is the toroidal field. And the hydrodynamic problem, which is a classic problem in instability theory, is right on the horizontal axis right there. And what you can see is this regime diagram. This is now as a function of the horizontal wave number, H. You can see it breaks up into different domains. The unstable baroclinic modes are confined to the lower left. And if you get above a P of about 0.33, it's not unstable at all. It completely suppresses the baroclinic instability. And that corresponds in the tachocline to just a few kilogauss. So that's a very negative result as far as whether baroclinic instability is playing an important role. If it is, it's got to be outside the domain where the toroidal field is. Now, in the same plot, you can see that outside this necessary condition for instability in the middle, you get neutral alphane waves. So you get all these different modes operating in the same system. If you add the Coriolis parameter, so you now have Rossby waves in the problem, the stability diagram changes somewhat. You get two domains, one of which looks mostly like Rossby waves on the left, and then one on the right that's modified from what it was without the beta effect. And then you still get alphane waves, and I'll come to that in the next slide. I just want to remark in passing that back in the 60s, I actually built a Rossby wave dynamo for this from the toroidal field, which actually does work. Whether it applies to the sun or not is, I guess, an open question. This shows, by the way, how the baroclinic instability, how the neutral and unstable waves are. You can see now the alphane waves on the right, upper right, they have split into a slower mode and a faster mode. They're a mix of Rossby and alphane wave with mostly alphane characteristics. But on the extreme left in the diagram, these modes are basically pure Rossby waves, but they're all present in this system. Now, fast forward to 2017, I went back and did the problem again, this time with a full spherical shell. And here, most importantly, I did not assume that the perturbations are geostrophic, but to get something essentially analytical, what I did was to solve this on a cone, which cone is whose axis is coincident with the rotation axis of the object, and there's a tangent of that cone to a given latitude in a hemisphere, and then you treat that cone shape as if it were unfolded. You have all the curvature effects in, but you're not doing true spherical geometry. And what you see in the instability diagram on the right is you get two domains of instability. This depends completely on where there is a thermal wind, and you have a thermal wind of opposite signs, low latitudes and high, divided by the latitude where the rotation rate in the tachocline is the same as the rotation rate of the interior. So you get these, and these are all different wave numbers. They're all unstable. So there's a broad range that's unstable. And these are growth times on the right at high latitudes of a few months for e-folding growth, and more like a year to have in low latitudes. Now, what happens when you add a toroidal field to this? You can see that for all, now this is again, I'm using the same parameter, this effective gravity G, and for all G, you can see that the growth rates go down with the toroidal field increasing, whether you're in low latitudes or high, and in low latitudes, you've basically suppressed baroclinic instability by 1200 Gauss, and in the high latitudes by about 3500 Gauss. They started out with high wave numbers, but they get down to the lowest wave numbers. So again, even in the spherical system, baroclinic instability gets suppressed if the toroidal field is strong enough. This next one shows a regime diagram, I'll call it, where you have domains of instability and stability as a function of latitude and toroidal field strength. So you get these two separate domains which close off at the top. So if you had some intermediate field strength, you just get two bands of instability where the baroclinic effect was big enough to overcome that toroidal field. So this is a somewhat discouraging message vis-a-vis the tachocline, because it appears that baroclinic instability is unlikely to play much of a role there, at least when it comes to the parts of the tachocline that have significant toroidal field in them. And I think that argues in favor of looking back more at the MHD shallow water class of models for this. Okay, so that's so much for the global instabilities. Now let me talk about much smaller scale instabilities that relate to magnetic buoyancy and just the rotation, differential rotation in height of the sun. Interestingly enough, mathematically, the equations for this are identical to what I used in the baroclinic instability for the sphere, except we take the opposite limit in the latitudinal disturbance scale. Instead of treating it globally, we now take an extremely small scale. And what that does is it makes the thermal diffusivity of the system essentially infinite. And when that happens, then you have no thermodynamic equation and therefore no temperature perturbations in this system. And so the equation of state relates only to pressure with density. And in this limit, the Richardson number criterion for the instability of stratified shear flow, that is the Helmholtz instability, goes away. Now we also assume in this, as in Gilman 2017, the toroidal field peaks at mid-depth in the tachocline, and the differential rotation has a solar profile with latitude and is linear with height. So believe it or not, when you do all those things, the perturbation equation is reduced to a single quartic algebraic equation. And so that we have results at several levels here. This first slide shows what you get when you have no magnetic field and you have what I would call pure rotational instability. And what's happening here is you displace a fluid ring, and it doesn't have to be axisymmetric. It can have any longitudinal wave number. And at high latitudes, it's unstable, as you can see. In low latitudes, it's stable. What's going on there? Conservation angular momentum is governing here. So at high latitudes, that fluid element rising encounters a lower rotation, and therefore it continues to go up. At low latitudes, it encounters a higher rotation, and it falls back. Now, a very interesting result from this is, and this was sort of a particular assumption about the tachocline depth, which was actually 4%. If you look at the diagram on the right, you can make an argument that maybe this actually goes on in the sun, and the tachocline thickness increases with higher latitude until you reach marginal instability. And that plot on the right is actually what the thickness would be for marginal instability. And you can see starting from 0.04, but when you get to the pole, it's 0.14. In other words, it's 14% of the radius. So this hint from observations that the tachocline is prolate and is thicker in high latitudes, I think has some theoretical support for it. Now, if you go to magnetic buoyancy instability, and I'll leave out the rotation for a minute, then you find out that all wave numbers are unstable at all latitudes with an amount that varies with latitude and the field strength. And they're very fast. If I can see this better, you can see the growth rates over here of the e-folding times. At the bottom, you're at 20 days. The top, you're at 2 days. So this is very fast instability. Now, this instability occurs only in the upper half of the tachocline, where the toroidal field is declining with height. Now, the energy for magnetic buoyancy is coming from that extra mass in the reference state, supported by the magnetic field gradient, compared to the mass present without a magnetic field. Now, you add rotation to this, and what you do is you stabilize it much more at low latitudes than at high. This is for different field strengths here now. These little numbers are the most unstable mode, and they're getting smaller as you go towards the pole, not surprisingly, because the linear dimensions are getting smaller. But you see here how fast these things are. 0.01 years, that's just 3 days up there. the physical explanation is the Coriolis forces are opposing the vertical motion most strongly at the equator and not at all poles. The decline of the most unstable M is just due to the shorter latitude surface. The Maxwell stresses that oppose magnetic buoyancy are proportional to M. So you need a smaller M at high latitudes to maximize the growth rate. Now, if you make it another sort of an instability diagram for the whole domain, you can see it for all high latitudes, all the way down to 0 where it's unstable. But in low latitudes, there's a stable domain until you get a sufficiently high toroidal field. This, I submit, is extremely suggestive of what's going on in the sun with the latitudes where sunspots form, because this instability, magnetic buoyant instability, has to get above this threshold at that latitude. And that threshold goes down as you go up to high latitudes, but its width is very similar to the domain of sunspots that we actually see. And that may be an explanation of why sunspots are only seen in low latitudes. Now, in high latitudes, there's instability even for very weak magnetic fields because the stabilizing effects of the Coriolis forces fall and the radiative differential rotation itself can be unstable. And this is where, so this is now magnetorotational instability, and it's, Valvis Hawley is more or less the same thing. Now we're seeing at these high latitudes, even this is a toroidal field of 30 Gauss. And you can see the growth rates here. And so it's the high wedge numbers that are really most unstable. And the growth rate, these things are, again, pretty fast. And if you get up to say 300 Gauss, and you're talking the high wedge numbers, you're talking in just a few days growth. Well, this, I submit, that this is what's happening in the high latitudes of the sun. It makes it very hard to generate strong toroidal fields in high latitudes by dynamo action, because this stuff's going to break up and come out at very high wedge numbers. And I suggested in the paper that maybe this explains the continual emergence of ephemeral active regions that we see at high latitudes. So to summarize, the Tachocline latitudinal differential rotation is stable to 2D HD disturbances. The shallow water global disturbances do destabilize Tachocline differential rotation. The smaller latitudinal differential rotation becomes unstable when the toroidal field is added to 2D and shallow water models. Baroclinic instability of the thermal is suppressed by even relatively weak toroidal fields. Hydrodynamic disturbances of very small latitudinal scales destabilize the vertical differential rotation of high latitudes, but not low, due to conservation of angular momentum. Adding a toroidal field to the reference state destabilizes the high latitude differential rotation for all vertical differential rotations and even for weak toroidal fields. And adding a toroidal field destabilizes low latitudes via magnetic buoyancy instability if the toroidal field is larger. So the future. Well, I would say this is all linear studies that you saw with very small exceptions. So I think one of the things for the future clearly is what are the nonlinear consequences of all these instabilities in their various combinations? Well, as far as the global problem is concerned, I would say in some sense the future is already here, and I've listed some of the things that have been done. Ducati 2012, the nonlinear HD shallow water model demonstrates the existence of oscillations between latitudinal differential rotation and Rossby. And the 2017-2018 papers, the discovery of Tachocline nonlinear oscillations and their role in amplitude and patterns of magnetic activity seen on timescales of 6 to 18 months, perhaps explaining the existence of seasons of solar activity within the sunspot cycle. Ducati and McIntosh 2020 described the central role of MHD Rossby in simulation and prediction of space weather. And in Ducati et al. 2021A, infer the shape of the Tachocline toroidal field from surface magnetic activity observations. You can actually infer with some assumptions about how the toroidal field departs from a pure toroid into something that has longitudinal structure. And then most recently, demonstrating a nonlinear effect of this mixed stress, which is so powerful if it's strong enough it can actually take a toroidal band and split it in two along its own axis. And that may provide an explanation for the latitude width of a butterfly diagram, because as you know, the butterfly diagram has width because there are obviously spots coming up at later times at higher latitudes than earlier spots. Otherwise, it would be a line and they'd always be going towards the equator, but it's not. It's got a finite width. Now, by contrast, I would say the study of nonlinear effects of magnetic buoyancy and magnetic rotational instability is just beginning. And then finally, it's unclear to me whether nonlinear effects of baroclinic magnetic instability will be important for understanding the tachocline. That's it. Thank you. Oh, and I also, for those, I welcome anyone who would like a full set of these slides. I went kind of fast. This is the list of all the publications that I referenced in the talk to help if you wanted to dig into things further.
That's awesome. Thank you, Peter. Thanks very much. Questions for Peter? Yeah, jam boards too. You've stunned everyone, Peter.
I had a question about alpha effects. I mean, given that all these instabilities might be operating in the tachocline, do you have a preference for, you know, is the production of colloidal field from toroidal field happening close to the surface, as in a classical flux transport dynamo in the bulk of the convection zone, or could everything really be happening in the tachocline?
Well, it's clear that you can get an alpha effect out of almost all these instabilities. Certainly in the baroclinic case, and that's how I built that simple Rossby wave dynamo. You get kinetic helicity there. In the shallow water, yes, you can get kinetic helicity there. What's unclear to me is whether you can have a dynamo which is confined to those layers, or whether it's a combination of what's happening in the tachocline with what's happening above. I mean, I think no one can deny the existence of that surface alpha effect because you can observe it. But that's in a different domain, and there's nothing to prevent you from having different alpha effects at different depths. So I think it's a kind of an open question. I mean, you may even have more than one dynamo in some sense. You may have some dynamo action near the bottom of one type and dynamo action above that, you know, or it's all coupled together. And the meridional circulation helps within the convection zone, helps to keep the various parts synchronized.
Okay, thank you.
Sasha?
Peter, thanks for a very interesting talk. I have a question about how we can test in observations your theory, and not just some kind of speculations about the seasons of activity, but we have some measurements of, say, torsion oscillations. Is there any effects of these instabilities on torsion oscillations, or say in variations of the sound speed, aspherical variational sound speed in the tachocline that we can measure by heliosismology?
Let me see if I understand what you're asking. You're asking, do any of these instabilities produce torsional oscillation?
No, I'm asking how can we test in observations your theory? And in observations, we can measure torsion oscillation, zonal flows, and possibly all the way to the tachocline.
Oh,
what would be your prediction for these measurements? And also, presumably, someday we can measure also variations of the temperature variations, maybe not direct of magnetic field, but we see some asphericity in sound speed. And what will be your prediction for such measurements? How can we test your theory?
I'm still not quite sure I know what you're asking. Can we deduce properties of the perturbation fields from heliosismology? Is that I'm groping here? I know I'm aware that the torsional oscillations may go all the way to the bottom.
Yeah, but how it relates to your theory, these variations? Is there any way to use for testing of your theory?
Oh, you mean predict what a heliosismologist should observe?
Yes, yes.
Well, that's the why I was asking the question about Rossby waves, because, you know, certainly for the global instabilities, they all, one way or another, have some properties of Rossby waves in terms of longitudinal propagation. You know, we know something about from the nonlinear theory about the amplitudes to expect. I think we're talking about RMS velocities there of a couple of tens of meters per second. But as far as the magnetic field is concerned, as everybody has said, it takes an extremely high field to see a perturbation in the measurable from helioseismology. So, and that's one reason I was asking about, can you see Rossby waves in the, now maybe some thermal anomaly associated with them that you could pick up, I don't know. But certainly what the theory says is that you should see that there will be Rossby waves there, MHD Rossby waves, not just where the toroidal band is, but particularly on the equatorward side of it. You should see velocities, but not magnetic fields particularly, and relatively low wave numbers. And then, you know, the propagation will be some combination of the natural Rossby wave propagation retrograde and the effective differential rotation sweeping it forward or back depending on the latitude. So that's what you got. But I gather from the helioseismologist earlier that it's going to be very hard to pick that up because it's low spatial resolution and you have to average over so much time that you can't see them.
Did you put your hand up again, or was there? Yeah. Okay. Sorry, Gustavo. I think you had your hand up, right?
Yeah. What about non-axisymmetric magnetic fields? Wouldn't be the manifestation of these instabilities in the Tachocline if they have a mode like m = 1 or something like this?
You mean additional instabilities on the non-axisymmetric part?
No, I'm continuing with Sasha's question about possible observations.
Yeah.
Of all of these instabilities. So the observing non-axisymmetric magnetic fields at the surface is not a manifestation, perhaps, of these MHD instabilities at the bottom.
Entirely likely. Yeah, I do. I mean, the wave number, the longitudinal scale is similar. Now, Rossby wave, you know, these instabilities are their structure and longitude is certainly larger than, say, the width of an active region, but that's a flux emergence issue. But we could start from a toroidal field protrusion into the convection zone, which has a larger scale, but then the emergence part comes from only a short segment of it. Oh yeah, I mean, the fact we do see global scale longitudinal dependence for the field, I think is clearly very likely connected to similar global scales at the Tachocline. Absolutely. Yes.
I mean, do you have an estimate of what, I mean, I know there's lots of instabilities going on here, but what are the most common longitudinal scales?
Well, I think there are two distinct ones. Certainly for the global ones, we're talking, and because in the MHD case, it does depend on how narrow that toroidal band is, but for, you know, plausible widths, say 10 degrees, you're talking wave numbers 1, 2, 3, possibly 4. That's about as high as you go.
Right, so not super high, but you know, you definitely have some longitudinal
Then
variation.
of course, the other instability I was talking about, magnetorotational, you know, it loves very small scales. I think if you look at the original Dalbus-Hawley theory, it's very similar. I mean, the differential rotation is shearing all those fields, but it's taking energy right out of it. And all those high wave numbers are unstable. And the ephemeral active regions I was referencing, they're quite small scale on the surface, and they're all over the place. I think it's a big issue for the dynamo. How do you build a toroidal field big enough in high latitudes that it gets to low latitudes and produces spots?
Yeah, interesting. I mean, sorry, this is my own question now. I mean, it seems, I mean, over many years, you've presented evidence that it, I mean, would you say that it's almost guaranteed that the tachocline is turbulent?
Well, maybe it depends on your definition. I think it's certainly not, it's certainly got global structure in it, which is time varying. Now, it depends on what you want to call that turbulent. On a global scale, yeah, on some time scale, yes, I would say so. But it may not be, you know, as vigorous as you might see in a, you know, in a small scales. But I can't imagine it's just differential rotation and radial circulation and straight toroidal field. I think that's extremely unlikely.
Yeah, that was kind of my follow-on question. Well, I guess there's two sort of follow-on questions. I mean, first of all, do you imagine, I mean, like you said, it's hard to know what you mean by turbulence in this thing, but first of all, you know, how strong do you expect this to be compared to like convective turbulence, for example? And then secondly, I mean, what level of anisotropy do you expect to see in these things?
Well, okay. Well, I mentioned, I think plausibly, and the nonlinear models give you some idea about this, that the low wave number Rossby wave type velocities would be a couple of tens of meters per second typically, which might be somewhat lower than the convective overshoot velocities. Although I've seen estimates that range all over the place on that. But they're not going to be hundreds of meters per second, no way. There's just not enough energy there to produce such a large field. And then and the fields associated with that are going to be, you know, some fraction of the sort of average toroidal field, but they're not going to, I mean, it's clear from the observations that you retain that toroidal structure well enough that Hale's polarity law is virtually always satisfied. So that puts to me an upper limit on how contorted the toroidal fields can become, which means that puts a ratio on the strength of the departures from toroid to the toroid itself.
Yeah, I think that's one of the, well, you know, plus everything has to get processed through a whole convection zone and a near surface shear layer before we have those observations. That's always the bit that gets me, because I'm with you. You know, you create strong toroidal structures, they'll be sort of mildly perturbed and so like that. They won't give you the scales that you see at the surface, but then it has to go through all this mess, right? So who knows what the hell happened.
But that's partly why I think the magnetic buoyancy instability is interesting, because that's on much smaller scales, and it's very fast. You know, by comparison with the 2D MHD instability at the base, which is time scale in several months, the typical magnetic buoyancy for a 10 kilogauss field, the e-folding growth time is a small number of days. So there's plenty of, and it will produce a pretty good wide range of longitudinal space scales, but not dominated by the highest. That's to say, depending on your parameters, the wave number for the most unstable magnetic buoyancy mode might be 6, 8, whatever it is. It would be smaller on scale generally than for the global instabilities due to horizontal differential rotation. Now you can at least imagine it getting down to the scale, towards the scale of the emergence of an active region, but it's probably bigger than that.
Krishnendu had a comment. Do you want to speak it, Krishnendu, or shall I read it?
Yeah, hi. So I just want to mention that since you are talking about like how deep we can detect Rossby waves, so using helioseismic mode coupling analysis, we found that Rossby waves can be detected till 0.88 solar radii. But below that, it is very hard to detect because background noise is strong enough, and so it cannot be like amplitude of Rossby waves does not stand out.
Yeah, I'm not surprised. It's discouraging, but it is what it is.
Yeah, this is a real shame because it sounds like detection of Rossby waves deeper down, it would be a really awesome thing, right?
It would, but everything I know about it, and I know far less than most about the Hughes seismology, it's going to be extremely hard.
Yeah, I'm also interested in your Rossby wave dynamo. I have to go back and dig that one out. I'm surprised that Lauren isn't asking you questions about that, because he sort of sees inductive action in his simulations, even down deep in the radiated zone, right, Lauren? And that's a fully nonlinear global spherical shell.
It is. It's limited.
Yeah.
Limited number of degrees of freedom, but it is fully nonlinear.
Lauren, do you want to comment on that one? Sorry, I called you out.
No, no worries. Yeah, no, I am curious about that. I mean, in my case, I can't really say with certainty if the Rossby waves are what are doing things. But I mean, I guess you looked at Rossby waves, these were just in the convection zone, is that right?
At the time I was doing the thesis and what followed after it, because we didn't know about the tachocline, and I was making arguments about a domain within the convection zone that, because of nonlinear convective effects, might be subadiabatic. There was some laboratory evidence of that kind of thing. And in fact, that idea has popped up again sometime in the last decade, that due to the not overshooting exactly, but due to nonlinear effects, you could get a bottom part of the convection zone that's actually subadiabatic to longer timescale perturbations, which would take you back towards the conditions that you want for baroclinic instability. But it's a very turbulent medium though, so it's a complicated situation.
So how, I mean, Rossby waves, I guess, are mostly 2D. I guess if they're entirely 2D,
then you won't get a dynamo. But that's the thing about baroclinic waves, they have the vertical motion, even if it's small. And so you get kinetic helicity from the correlation of the local vertical component of vorticity and the vertical motion. And that's very clear. That's exactly what was going on in that simple Rossby wave dynamo that I did. It was built, I used the same kind of equations and expansion that Ed Lorenz did for a lot of his famous work on limit cycles and deterministic chaos, all that. Very similar idea. And you can get into questions of convergence of that dynamo if you add more modes, but I didn't go there.
Okay. In the radiative interior, though, where, I mean, it's strongly stably stratified, I mean, could the baroclinic instability help you get more vertical motion when the stable stratification is so strong? Or
well, it could be. You have to have some vertical motion in order to release the energy. I've not seen a systematic study, and I may have just missed it, systematic study of baroclinic instability in a radiative interior of a rotating star.
Okay.
But I think that the subadiabatic stratification is it requires the particle trajectories to be very nearly horizontal. And to release the energy in baroclinic instability, they have to have some tilt with latitude in order to do that. And it's very hard to get that if the static stability is so high, which is typical of a radiative interior. But I'm not saying it shouldn't be looked at.
Okay, awesome stuff. Anyone have a last question for Peter? I think all the ones on the jam board have been asked at this point.
You are mute, Nick.
Oh, yeah, off you go, Gustavo. Sorry.
I have just curiosity. What is the difference between what you call the tipping or the clamshell instability to the Tyler instability?
Which one? What was the last one?
Tyler. With E.
Tiger? No.
Taylor.
Tyler.
Taylor, Peter. Taylor instabilities.
Oh, I didn't mention Taylor instability. I think they're different partly because the original tipping instability, it's 2D and there's no stratification in that at all. I mean, it's all that's happening there is that a ring of toroidal field, if you give it a push, it will reach some finite amplitude equilibrium where it's oscillating and the whole thing precesses. Doesn't break up, doesn't do anything like that. And the clamshell is, the only difference between the two is the width of the original toroidal field. You need to have a band to get the tipping instability. If you have a broad toroidal field, then you got that clamshell effect, which almost certainly is not happening in the sun, as far as we can tell. Tipping instability, I think, is entirely possible in the sun. I suppose it's just one more argument that the latitude extent of the toroidal field at any given time is probably not that great. I mean, 10 degrees, full width at half maximum, something like that.
So you expect more of a band rather than an extended layer?
Well, extended in latitude.
In latitude, yeah. You expect only a band of 10 degrees or something like that.
I do. Yeah, I mean, to get, and you get very naturally how you get a, if you have this band migrating towards the equator with time, in the solar cycle, then it's fairly obvious source of flux coming into the surface. If you're starting with a very broad band that kind of fills the hemisphere, then what gives you the migration towards the equator with time? It has to go to a different part of that original extremely broad band at a later time. But then to get a width in the butterfly diagram, you have to be getting it both on the polar side and the equatorward side of the maximum. Whereas if you have a band that has limited latitudinal extent that's migrating, it's very natural.
Yeah, I agree with what you say, but the differential rotation is continuous. How could you expect to form a band and not an extended layer?
Well, I understand that's a very reasonable issue to ask.
Okay, let's just let Sushant ask a last question and then we'll take a break for lunch. Sushant?
Hi, Peter. Thank you for the broad perspective on all the instabilities. I wanted to ask you, which of these two do you think plays a major role in creating the toroidal field? Is it the radial shear in differential rotation, or is it the latitudinal shear in differential rotation?
I'm not sure you can answer that question from the instabilities, but I would say from considerations, I would say it's mainly the latitudinal shear. That's the one that, you got this broad differential rotation profile. You can wind it up for a long time. But it could also be that the alpha effect plays some role. The traditional alpha omega dynamo, the alpha effects only producing toroidal field, but the so-called alpha squared omega dynamo can produce both colloidal and toroidal field.
All right, thank you.
Okay, it's exactly noon in Pacific time, California time, from this very selfish perspective. It's lunchtime. So sorry, everybody else who's in a weird different time zone where it's not lunchtime, but we're going to call it lunchtime. Thanks again, Peter, for an amazingly comprehensive talk and an explanation of all that.
If anybody would like I'd be happy to send the full set of PowerPoint if anybody would like them. And as I say, the last page has all the references if you want to dig into the papers further.
Yeah, awesome. I think we're going to try and collect slides from all the speakers. But thanks for all the speakers, for Charles and from Ansgar, who's probably disappeared sensibly. And we'll begin again this afternoon at 1 o'clock Pacific time. So in an hour from now. So take a break, get some lunch or whatever you would do at your time.